Imagine two particles, perhaps electrons or photons, that have interacted with each other in such a way that they become fundamentally linked, connected by an invisible thread that persists regardless of the distance separating them. And when you measure a property of one particle, instantaneously the other particle's corresponding property becomes defined, as if the universe itself is sending an instantaneous message across space. Violating everything we intuitively understand about how information should travel. This phenomenon, called quantum entanglement, represents one of the most profound mysteries in physics, a situation where two particles exist in what scientists call a superposition, a state where they simultaneously possess all possible values for a given property until the moment of measurement. And yet the moment you observe one particle and find it spinning clockwise, the other particle, which might be on the opposite side of the galaxy, will instantly be found spinning counterclockwise. A correlation so perfect that it seems to defy the fundamental principle that nothing can travel faster than light. The mechanism underlying this phenomenon emerges from the quantum mechanical framework itself, a mathematical description of reality at the smallest scales where particles do not behave like tiny balls with definite positions and velocities, but rather like waves of probability. And when two particles become entangled through interaction, their quantum states become mathematically inseparable, described by a single wave function that encompasses both particles as a unified system. Meaning that neither particle truly has its own independent state until measurement forces reality to collapse into a definite configuration. What makes this even more conceptually troubling is that Einstein himself, one of history's greatest physicists, found this phenomenon so philosophically disturbing that he called it spooky action at a distance and insisted there must be hidden variables, additional information we were not accounting for, yet decades of experiments, particularly the tests of Bell's inequality conducted in the 1980s and refined continuously since then, have demonstrated with overwhelming precision that no local hidden variable theory can reproduce the predictions of quantum mechanics, meaning the universe genuinely does appear to operate in this strange, interconnected way. Imagine a laboratory where light travels through two narrow openings in a barrier, and on the other side, a detector screen waits to record where each photon arrives. And what physicists discovered when they set up this seemingly simple apparatus has fundamentally challenged our understanding of reality itself. Because when they weren't watching, when no measurement device was in place to determine which slit the light passed through, the particles behaved like waves and created an interference pattern on the screen. A pattern that suggested each photon somehow traveled through both slits simultaneously and interfered with itself. But the moment they installed a detector to catch the light in the act of choosing one slit or the other, the particles immediately changed their behavior and acted like particles instead, abandoning the interference pattern and creating two distinct bands on the screen as though they were tiny bullets fired through independent openings. The mechanism underlying this perplexing phenomenon appears to rest on the fundamental nature of quantum probability and observation itself, because at the quantum scale, particles exist in what physicists call a superposition, a state where they are not definitively one thing or another until measured, and the act of measurement forces reality to collapse from this probabilistic cloud into a single definite outcome. So the light wasn't being coy or avoiding observation. But rather the universe itself operates on a principle where unobserved systems behave according to wave functions that describe multiple simultaneous possibilities, while observed systems must declare themselves, must crystallize into singular reality. And this interpretation suggests that consciousness or measurement doesn't create reality so much as it forces reality to commit to one version of itself. Yet despite decades of experimental verification and the mathematical precision with which quantum mechanics predicts these outcomes, we have normalized and accepted a state of affairs that should perplex us far more than it does, because the idea that reality fundamentally depends on whether anyone is looking, that observation alters the very fabric of what is and is not, remains philosophically unsettling even as we treat it as established fact in our physics textbooks and our technological applications. And we proceed through our days building quantum computers and understanding atomic behavior while maintaining a cognitive blind spot about the truly disturbing implications of what this experiment tells us about the nature of existence itself. Imagine a scientist standing in front of a wall where millions of tiny particles are being fired one at a time through two narrow slits, and behind that wall sits a screen that records where each particle lands, creating a pattern over time. When no one is watching, when no measurement device is in place to determine which slit the particle passes through, the particles behave in a peculiar way, spreading out across the screen in an interference pattern that suggests each particle somehow went through both slits simultaneously, as though it existed in multiple states at once. The moment the scientist decides to install a detector, a measurement device designed to catch the particle in the act and determine definitively which slit it actually passed through, something remarkable happens. The particles suddenly change their behavior entirely. They stop creating the interference pattern and instead produce two distinct bands on the screen, as though they had made a conscious decision to pass through one slit or the other, as though the act of being observed fundamentally altered their nature. This phenomenon, known as the observer effect, reveals something that challenges our basic intuition about reality itself, that the act of observation is not passive, not merely a neutral recording of what already exists, but rather an active force that participates in determining what actually occurs. The mechanism behind this strange behavior lies in the quantum realm, where particles exist in what physicists call superposition, a state of fundamental uncertainty where they genuinely do not have definite properties until measured. When a measurement takes place, the particle's wave function collapses into one specific state, one specific outcome, and this collapse is triggered by the very act of interaction required to gather information about it. The detector must interact with the particle to know where it is, and that interaction fundamentally changes the particle's trajectory and behavior. This is not deception or illusion, it is the actual nature of how reality works at its most fundamental level. What makes this effect so profoundly strange and deeply unsettling to contemplate is that it seems to suggest consciousness plays a role in determining physical reality, that the universe does not have fixed properties independent of observation, that existence itself is somehow relational rather than absolute. Imagine standing in a darkened room where a particle exists in every possible state simultaneously until the moment you look at which point reality crystallizes into a single definite outcome, as though the universe itself has been waiting for your observation to decide what is actually true. This is the peculiar phenomenon known as wave function collapse, one of the most intellectually unsettling discoveries in quantum mechanics, and it presents us with a deeply strange picture of how reality actually works. In the quantum realm, particles do not occupy definite positions or possess definite properties until they are measured or observed, existing instead in what physicists call a superposition, a ghostly mathematical combination of all possible states expressed through something called a wave function. When a measurement is made, this wave function abruptly collapses into a single concrete state, and suddenly the particle has a definite position, a definite momentum, a definite spin, or whatever property was being measured. The mathematics of quantum mechanics describes this process with extraordinary precision, allowing physicists to calculate probabilities with stunning accuracy, yet the mechanism itself remains philosophically perplexing, because the act of observation seems to fundamentally alter reality rather than simply reveal what was already there. The Copenhagen interpretation, one dominant framework for understanding quantum mechanics, suggests that particles genuinely do not have definite properties until measured, that the wave function represents only our knowledge or probability of outcomes, and that the act of measurement necessarily disturbs the system in an unavoidable way. Yet this creates a troubling question that has haunted physics for nearly a century. Does consciousness play a role in collapsing the wave function, or is measurement simply any physical interaction that extracts information, whether or not anyone is observing? The measurement problem, as it is called, represents a deep gap between our theoretical understanding and our intuitive grasp of reality. We have come to accept this inexplicable mechanism as simply how nature operates at the quantum level, teaching it to physics students worldwide as though it were an established fact rather than an unsolved mystery that strikes at the very heart of what reality means. Imagine a sealed box containing a living cat, a radioactive atom, a Geiger counter, and a mechanism that will release poison if the atom decays. Once the box is sealed and we cannot observe what is happening inside, quantum mechanics tells us something deeply counterintuitive occurs. According to the mathematical formalism of quantum superposition, the radioactive atom exists in a state of both decayed and not decayed simultaneously until the moment we open the box and make an observation. This means, by extension, the cat inside would theoretically exist in a superposition of both alive and dead at the same time, suspended in an impossible middle ground between two mutually exclusive states. The cat only becomes definitively alive or dead the instant we lift the lid and collapse the quantum wave function through the act of observation itself. This thought experiment emerged in 1935 when physicist Erwin Schrödinger proposed it as a critique, a reductio ad absurdum designed to highlight the apparent absurdity of applying quantum superposition rules to macroscopic objects in the everyday world. He was pointing out that while quantum particles might exist in superposition, obviously a cat cannot be both alive and dead simultaneously, yet the mathematical logic of quantum mechanics seemed to demand exactly this conclusion when scaled up to larger systems. The psychological mechanism that makes this thought experiment so persistent in our collective imagination stems from the fact that it exposes a fundamental gap between what our intuition tells us about reality and what the mathematics of quantum mechanics appears to require. We live in a world of clear, observable facts, where things are definitively one way or another, yet this experiment demonstrates that at the subatomic level, reality seems to resist such certainty until observed. The thought experiment persists despite having no actual application to real cats because it brilliantly crystallizes our discomfort with quantum indeterminacy itself. Scientists and philosophers continue to reference it, debate its implications, and publish papers about what it means, even though Schrödinger himself intended it to demonstrate why we should not apply quantum rules to macroscopic objects. We have somehow normalized this paradox as a fundamental feature of how nature works, accepting that observation itself shapes reality at the quantum level, even as the larger implications remain deeply unsettling and unresolved in our understanding. Imagine a ball rolling toward a hill, a ball that simply does not have enough energy to reach the top, yet somehow, inexplicably, it appears on the other side of the hill without ever climbing over it, without any visible path around it, without any rational explanation that our everyday experience can provide. This is the essence of quantum tunneling, one of the most profoundly counterintuitive phenomena in the physical universe, a process that occurs constantly at the subatomic level despite violating our deepest intuitions about how reality should function. At the quantum scale, particles behave in ways that seem to defy the classical laws of physics that have governed our understanding of the world since Newton's time, and quantum tunneling represents perhaps the most vivid example of this fundamental strangeness. When a particle encounters an energy barrier that it theoretically cannot overcome, such as an electron approaching a wall of electrical potential that should repel it, the particle does not simply bounce back as our intuition demands it should. Instead, there exists a measurable probability that the particle will spontaneously appear on the other side of that barrier, having passed through it as though the barrier were not there at all, a phenomenon that has been observed and verified thousands of times in laboratories across the world. The mechanism behind this baffling behavior emerges from the wave nature of matter itself, a concept that revolutionized physics in the 20th century when scientists realized that particles are not solid little spheres, but rather exist as probability waves, as clouds of likelihood spread across space rather than occupying single definite positions. According to quantum mechanics, every particle is described by a wave function, a mathematical expression that tells us the probability of finding that particle at any given location, and this wave function does not abruptly become zero at an energy barrier as classical physics would predict. Instead, the wave function extends through and beyond the barrier, decaying exponentially but never quite reaching absolute zero, meaning there's always some small but real probability that the particle exists on the far side of the barrier even when it lacks the energy to climb over it. When we measure whether the particle is indeed on the other side, we collapse this probability wave into a definite position, and sometimes, though not always, that position is beyond the barrier. On August 15, 1977, a radio astronomer named Jerry Amon was conducting a routine survey at Ohio State University's Big Ear Radio Telescope, a massive instrument designed to passively listen to the cosmos in search of any signals that might indicate extraterrestrial intelligence, when he noticed something extraordinary emerging from the data stream. A signal so unusual and so perfectly anomalous that he circled it on the computer printout in red pen and wrote the word "wow" in the margin, a single exclamation that would define one of astronomy's most enduring mysteries and captivate the imagination of scientists and the curious public for nearly 5 decades. The signal appeared to come from a location near the Chi Sagittarii star group, exhibiting a narrowband transmission on the hydrogen line frequency of 1420 MHz, a wavelength considered particularly significant because it is the natural emission line of hydrogen, the most abundant element in the universe, and therefore a logical frequency for any advanced civilization attempting to broadcast a message across interstellar distances. What made the WOW signal so remarkable was not merely its existence, but its characteristics. It was strong and unmistakable, arriving with such clarity and definition that it stood out dramatically against the normal background radiation of space. Yet when subsequent observations were conducted in the following nights and weeks, the signal could not be relocated or replicated, vanishing as mysteriously as it had appeared, leaving behind only that single, tantalizing recording and the indelible memory of those 37 seconds of detection. The phenomenon exemplifies humanity's eternal yearning to find evidence that we are not alone in the universe, a psychological need so profound that we remain captivated by even the most ambiguous and potentially explicable data. For the signal could have originated from numerous terrestrial sources, including satellite transmissions, military communications bouncing off the ionosphere, or interference from nearby equipment, yet the very possibility that it might have been something more. Something genuinely extraterrestrial in origin captured our collective imagination in a way that has scarcely diminished across the intervening years. Imagine looking out at the night sky and seeing billions of galaxies spinning, orbiting, and moving in ways that should tear themselves apart according to everything we understand about physics and gravity, yet they persist in their motion with a stability that defies explanation. When astronomers began measuring the rotation speeds of galaxies in the 1970s, they discovered something profoundly troubling. The outer regions of galaxies were moving far too quickly relative to the amount of visible matter we could detect, which should have meant these cosmic structures would fly apart like a child's spinning top suddenly let loose. The mathematical calculations were clear and inescapable. The gravitational pull from all the stars and gas we could see was simply insufficient to hold these galaxies together at the velocities they were traveling. Yet the galaxies remained intact, cohesive, and stable, suggesting that some invisible, undetectable form of matter was providing the missing gravitational anchor. This invisible substance became known as dark matter, and it comprises roughly 85% of all the matter in the entire universe, vastly outweighing every star, planet, atom of normal matter that we can observe and measure with our instruments and telescopes. The psychological mechanism at work here involves the collision between our empirical observations and our mathematical models, creating a cognitive dissonance that scientists resolved not by abandoning observation, but by accepting the existence of something fundamentally undetectable through conventional means. We could not see dark matter, could not touch it, could not capture it in any laboratory experiment, yet the gravitational effects were undeniable, measurable, and consistent across countless observations. The human mind, when confronted with such evidence, gravitates toward accepting the invisible rather than doubting the observable, because the mathematics does not lie. We had reached the limits of our sensory apparatus and our technological extensions thereof, and we were forced to accept that reality contains layers we cannot directly perceive, dimensions of existence that operate beyond our ability to detect them directly. What makes this persistent despite its seemingly illogical foundation is that dark matter has become so thoroughly woven into our understanding of cosmology that we now treat it as foundational rather than provisional. Entire branches of physics have been constructed upon its existence. Imagine standing in complete darkness, unable to see anything around you, and yet somehow knowing with absolute certainty that something invisible is pushing everything away from you at an accelerating rate, something so fundamentally powerful that it comprises nearly 70% of all existence in the universe, and yet we cannot touch it, measure it directly, or even begin to understand what it truly is. This is the reality of dark energy, one of the greatest mysteries in modern physics and cosmology, a force that defies our most basic intuitions about how the universe should behave. In the late 1990s, astronomers conducting observations of distant supernovae made a discovery so unexpected, so counterintuitive, that it fundamentally altered our understanding of cosmic expansion. They found that the universe was not merely expanding, as Edwin Hubble had demonstrated decades earlier, but was actually accelerating in its expansion, moving faster and faster as time progresses, as though some invisible hand were pressing outward on all of existence with ever-increasing force. This observation contradicted everything physicists expected based on gravitational theory and the mass content of the universe. Gravity should have been slowing down the expansion, pulling everything together, yet instead something was working against gravity, pushing everything apart with greater intensity. Scientists named this mysterious force dark energy, and in doing so, they essentially admitted that we had discovered something profoundly important about reality while simultaneously confessing complete ignorance about its nature. The mechanism behind why dark energy behaves as it does relates to the fundamental structure of spacetime itself and the quantum properties of the vacuum that pervades all of existence. One leading theory suggests that dark energy represents the energy of the vacuum itself, the constant background energy that exists even in the absence of particles, a kind of restless quantum sea that fills every infinitesimal point in space. According to quantum mechanics, empty space is never truly empty, but instead seethes with virtual particles constantly appearing and disappearing, and this quantum activity generates what physicists call vacuum energy, which creates a kind of pressure that pushes space itself apart. Another possibility involves a scalar field permeating the universe called the quintessence field, which dynamically changes across space and time and produces a repulsive force analogous to how electromagnetic fields generate forces between charged particles. Imagine a world where thousands of people remember something happening in a specific way, only to discover that reality contradicts their memory entirely, and yet their recollection feels so vivid and certain that doubt becomes almost impossible. This phenomenon is known as the Mandela Effect, named after the widespread false memory that Nelson Mandela died in prison during the 1980s, when in fact he was released, became president of South Africa, and lived until 2013. The effect describes those curious moments when large groups of people share identical false memories about events, products, or cultural moments that either never occurred or occurred differently than remembered. Consider the Berenstain Bears, a beloved children's book series that millions recall as being spelled Berenstein, with an E instead of an A memory so persistent that people have created elaborate theories about alternate realities and timeline shifts to explain the discrepancy. Or think of the famous Star Wars line that countless fans remember as Luke, "I am your father," when the actual dialogue is simply "No, I am your father," a subtle but significant difference that somehow lodged itself differently in collective consciousness. The psychological mechanism behind this phenomenon involves several interconnected cognitive processes, particularly false memory formation and confabulation, where the brain fills in gaps in recollection with plausible details that feel authentic. When multiple people share these false memories, the effect becomes amplified through a process called social reinforcement, where hearing others describe the same incorrect memory actually strengthens and legitimizes our own flawed recollection rather than correcting it. Our brains are not perfect recording devices, but rather constructive systems that constantly recreate memories based on schemas, expectations, and narrative logic, meaning we often remember not what actually happened, but what we expected to happen or what would make sense in the broader context of our understanding. The persistence of the Mandela Effect, despite widespread correction and evidence demonstrating the true facts, reveals something profound about human cognition and our relationship with certainty itself. We live in an age where information is instantly available, where one can verify claims with a simple search, and yet people encounter irrefutable proof that their memory is incorrect and still experience genuine shock and disbelief, as though the evidence itself seems somehow wrong rather than their recollection. Imagine the universe stretching infinitely across both space and time, governed entirely by the laws of thermodynamics and probability, where every possible arrangement of atoms has some non-zero chance of occurring if you wait long enough. Within this vast cosmic landscape, a deeply unsettling possibility emerges from the mathematics of statistical mechanics, one that challenges our very understanding of consciousness and existence itself. According to Ludwig Boltzmann's 19th-century work on entropy and probability, in an infinitely old universe with infinite time available, random molecular fluctuations could theoretically assemble themselves into conscious entities, fully formed minds that spontaneously materialize from the quantum foam and thermal chaos, experiencing a single moment of awareness before dissolving back into the void. These entities, now called Boltzmann Brains, represent a paradox so troubling that physicists have spent decades grappling with its implications. The mechanism underlying this concept operates through pure statistical mechanics. Given enough time, the random motion and rearrangement of particles becomes capable of producing any configuration, including one so improbably organized that it constitutes a thinking being. A human brain, after all, is simply atoms arranged in a particular pattern, and if atoms can arrange themselves randomly into any pattern given sufficient time, then consciousness itself becomes an inevitable product of mere chance. The disturbing implication follows logically. If the universe is infinitely old and infinitely large, then most conscious experiences in existence would not belong to beings like us who evolved gradually, but rather to these spontaneously fluctuating minds that appear and vanish in isolated pockets of spacetime. Yet this conclusion seems absurd and contradicts our observations entirely, leading physicists to question either the validity of infinite universes, the eternality of cosmic expansion, or the very premises upon which this reasoning rests. We live comfortably in a universe where our consciousness arose through billions of years of evolution, never once entertaining that the vast majority of minds in existence might be ephemeral statistical accidents. The persistence of this paradox, despite its logical coherence, illustrates how profoundly our intuitions fail when applied to infinite timescales and incomprehensibly large numbers, and how the universe might contain truths about consciousness that we have not yet learned to accept or even properly comprehend. Imagine for a moment that everything you perceive, every sensation you experience, every person you encounter, and every moment that unfolds around you is not fundamentally real in the way you assume it to be, but rather a sophisticated simulation running on some form of computational substrate beyond your comprehension. This concept, known as the simulation hypothesis, posits that our entire reality might be an artificial construct, a digital environment created and maintained by some form of advanced intelligence or civilization, much like how we might create immersive video games or virtual worlds within our own laboratories and computer systems. The hypothesis doesn't necessarily claim that this is definitely the case, but rather argues that given certain assumptions about technological progression and probability, the likelihood that we are living in base reality rather than in a simulation might actually be quite small. Consider the logical framework that supports this idea. If a civilization becomes sufficiently advanced, they would eventually develop the capability to run detailed simulations of conscious beings within computer systems. If such simulations become possible, then presumably they would run many of them, perhaps millions or billions of simulations operating simultaneously. If this scenario is true, then statistically speaking, any given conscious observer would be vastly more likely to exist within one of these simulations than within the single original universe that started it all. This is the core philosophical argument behind the simulation hypothesis, and it's remarkably difficult to refute with complete certainty. The psychological mechanism that makes this hypothesis so compelling and persistent is rooted in our deep uncertainty about the nature of consciousness and reality itself. We cannot directly observe the fundamental substrate of existence. We can only observe the patterns and laws that govern the world as we experience it. Physics has already revealed that reality at its deepest levels operates in ways that seem almost computational, with quantum mechanics suggesting that particles don't have definite properties until they are observed, and the universe operating according to mathematical laws that can be encoded into equations. Our brains themselves process information and create our conscious experience through electrical and chemical signals, which could theoretically be simulated. Imagine standing in a vast, incomprehensibly large cosmic landscape where galaxies, clusters of galaxies, and superclusters all seem to be inexplicably moving in the same direction through the universe, all streaming toward a region of space, as if pulled by an invisible gravitational force so powerful that it influences the motion of billions of galaxies across millions of light years, yet remains entirely invisible to our telescopes and instruments, defying our attempts to locate or even identify what it actually is. This is the Great Attractor, one of the most profound mysteries in modern astronomy, discovered not through direct observation, but through the peculiar motions of galaxies themselves, which revealed that our entire local universe is moving together in a coordinated way toward something we cannot see. In the 1970s and 80s, astronomers studying the cosmic microwave background radiation and the movements of distant galaxies noticed something deeply unsettling. The universe was not expanding uniformly in all directions as predicted by standard models of cosmic expansion. Instead, galaxies appeared to be flowing collectively toward a region of space located roughly 250 million light-years away in the direction of the Centaurus and Hydra constellations, as if the entire fabric of space itself contained a massive concentration of matter that was gravitationally drawing everything toward it. The mechanism behind this phenomenon relates to how gravity operates on the largest scales of the universe. Matter creates curves in the fabric of spacetime, and these curves guide the motion of other matter toward regions of greater density, much like water naturally flows downhill toward lower elevations. Because the Great Attractor is so distant, and because so much normal matter and dark matter exists between us and it, its gravitational influence propagates across unimaginable distances, gently but persistently pulling galactic clusters along with it. What makes the Great Attractor particularly mind-bending is that despite decades of investigation, astronomers still cannot definitively identify what causes it or even confirm its exact location and nature, as the region appears obscured behind vast clouds of dust and gas that prevent clear observation. Imagine standing at the edge of the most extreme object in the universe, a black hole so dense that not even light can escape its pull, a place where the laws of physics seem to collapse into themselves and reality becomes almost incomprehensible. For decades, scientists believed that black holes were truly black, that they swallowed everything that crossed their event horizon and offered nothing back to the universe, creating an absolute one-way boundary from which nothing could ever emerge. Yet in 1974, the renowned physicist Stephen Hawking made a discovery so counterintuitive and paradoxical that it fundamentally transformed our understanding of these cosmic objects and revealed that black holes are not actually black at all. What he found was that the space around a black hole, which we typically imagine as a perfect vacuum, is actually seething with quantum activity, a roiling sea of particle-antiparticle pairs constantly appearing and annihilating each other in what quantum mechanics tells us is a fundamental feature of reality at its smallest scales. Near the event horizon of a black hole, something extraordinary happens. One of these quantum pairs occasionally gets separated before it can annihilate, with one particle falling into the black hole while the other escapes into space, carrying away energy. This process, known as Hawking radiation, means that black holes are slowly evaporating, emitting particles and losing mass over extraordinarily long timescales, effectively creating a thermal glow that radiates outward from the event horizon itself. The mechanism operates through a subtle interplay between quantum mechanics and general relativity, two pillars of physics that normally work at different scales and rarely overlap. Yet here they collaborate in this remarkable phenomenon that seems almost impossible when you first learn of it. The smaller the black hole, the more intensely it radiates, which means it loses mass faster, which makes it even smaller, creating a runaway feedback loop that would eventually cause the black hole to explode in a final burst of radiation. This discovery created a profound mystery that physicists are still grappling with today. When a black hole evaporates completely, what happens to all the information about the objects that fell into it? Does that information disappear from the universe forever, violating fundamental principles of quantum mechanics, or is it somehow encoded in the radiation itself? Imagine standing in a completely dark room and realizing that everything you perceive as three-dimensional space around you might actually be encoded on a two-dimensional surface, much like how a hologram appears to have depth, but is fundamentally created from information stored on a flat plane, and this is precisely what the holographic principle suggests about our universe itself. The principle emerges from the work of physicist Juan Maldacena in the 1990s, who discovered a profound mathematical relationship between a theory of gravity in a higher dimensional space and a quantum field theory on its lower dimensional boundary, suggesting that all the information contained within a three-dimensional volume of space could theoretically be completely described by information residing on its two-dimensional surface. This means that what we experience as our vast, seemingly infinite three-dimensional universe, with countless stars, galaxies, and light-years of empty space, might be a projection or encoding of information that exists on some distant boundary at the edge of reality, much like how a movie projector creates the illusion of three dimensions on a two-dimensional screen. The mechanism behind this principle lies in fundamental properties of black holes and thermodynamics, particularly the discovery that black holes have entropy proportional not to their volume but to their surface area, which contradicts our intuitive understanding of entropy and suggests that information cannot be lost as completely as we once believed. This counterintuitive relationship between surface and volume became the key insight that led physicists to propose that the universe itself might operate according to the same principle, with all three-dimensional reality being fundamentally encoded on its boundary. What makes this principle so remarkable and persistent in contemporary physics, despite its profoundly strange implications, is that it has proven extraordinarily successful at explaining deep connections between seemingly unrelated areas of physics, providing mathematical frameworks that work with stunning precision and generating predictions that continue to hold up under rigorous scrutiny. Leading physicists worldwide to seriously consider that our direct experience of three-dimensional space might be an elaborate projection from lower-dimensional data, and yet we continue navigating our daily lives in complete comfort with this possibility, never questioning whether the depth we perceive in front of us actually originates from information encoded behind us. Consider the peculiar fate of information that falls beyond the event horizon of a black hole, that invisible boundary from which nothing, not even light itself, can escape once it crosses the threshold into oblivion. For decades, physicists grappled with a profound contradiction at the heart of quantum mechanics and general relativity, two pillars of modern physics that seemed fundamentally incompatible when confronted with the reality of black holes. When Stephen Hawking discovered in 1974 that black holes are not entirely black, but instead emit radiation due to quantum effects near the event horizon, he inadvertently sparked one of the deepest mysteries in theoretical physics. The paradox emerges from a simple but troubling observation. As a black hole radiates away its mass through Hawking radiation, it eventually evaporates completely, returning its energy to the universe as thermal radiation with no apparent connection to the information that fell inside. According to quantum mechanics, information cannot be destroyed. It can be transformed, scrambled, or hidden, but the total amount of information in a closed system must remain constant, a principle known as unitarity. Yet if a black hole evaporates completely and takes with it all knowledge of what fell inside, then information appears to have vanished from the universe entirely, violating this fundamental law. This creates a logical chasm that has haunted physics for nearly 50 years. The mechanism underlying the paradox involves the nature of entropy and thermodynamics at the quantum level, where the behavior of information becomes inseparable from the behavior of energy and matter. Black holes possess an entropy proportional to their surface area rather than their volume, a property so unusual that it demanded entirely new frameworks for understanding the relationship between gravity, quantum mechanics, and information theory. The mystery deepens when one considers that Hawking radiation appears completely thermal, carrying no information about the interior of the black hole, yet conservation laws suggest that information must somehow be preserved or encoded in ways we cannot yet detect. Remarkably, despite decades of intensive research and the emergence of string theory and holographic principles as potential solutions, the information paradox remains fundamentally unresolved in a way that satisfies all physicists equally. Imagine the universe as we know it existing in a state of precarious balance, a vast cosmic bubble floating in an infinite sea of possibility, and somewhere in the depths of theoretical physics exists a concept so profoundly unsettling that it suggests this entire bubble, along with everything within it, could simply cease to exist in an instant. This is vacuum decay, a phenomenon that emerges from our understanding of quantum field theory and the strange nature of the Higgs field, which permeates all of space and gives particles their mass. According to this theory, the vacuum state in which our universe currently exists might not be the lowest possible energy state, but rather a false vacuum, a temporary equilibrium sitting on an invisible plateau in an energy landscape, and somewhere far away in space or perhaps triggered by some unknown quantum fluctuation, a bubble of true vacuum could spontaneously form and begin expanding outward at the speed of light, fundamentally rewriting the laws of physics as it spreads. Within this expanding bubble, the Higgs field would settle into a lower energy state, and this transition would be catastrophic because the properties of all particles would change instantaneously. The fundamental forces would separate differently, atomic nuclei would destabilize, and chemistry as we understand it would become impossible, meaning every star, every planet, every living thing would simply unravel at the atomic level without warning or mercy. The mechanism driving this possibility lies in quantum mechanics itself and the strange mathematics of potential energy, where the Higgs field, like a ball rolling across a landscape, might be sitting in a local minimum that is not the absolute lowest point, and quantum tunneling effects or sufficiently energetic particle collisions could theoretically provide the nudge needed to set this catastrophe in motion. Imagine that the universe as we know it exists in a state of precarious balance, suspended in what physicists call a false vacuum, a condition so unstable and fragile that at any moment, without warning or fanfare, everything could suddenly shift into a lower energy state and trigger a catastrophic transformation that would remake reality itself from the ground up. This is the unsettling premise behind false vacuum theory, a concept that emerged from quantum mechanics and particle physics during the latter half of the 20th century, and it describes a phenomenon where the vacuum of space, which we typically think of as empty nothingness, might actually be poised at an unstable equilibrium, much like a ball balanced precariously at the peak of a hill rather than resting safely in a valley below. The mechanism behind this theory becomes comprehensible when we consider that quantum fields permeate all of space and time, and these fields possess what physicists refer to as potential energy levels, meaning that just as objects can exist in higher or lower energy states, so too can the fundamental fabric of reality itself. In our current epoch, we may be residing in what scientists term a false vacuum state, a higher energy configuration that is not actually the lowest possible energy state for the universe. And while this state remains remarkably stable, the laws of quantum mechanics tell us that there exists a probability, however infinitesimally small, that a quantum fluctuation could occur somewhere in space that would create a bubble of true vacuum. A lower energy state that would begin expanding outward at the speed of light. What makes this theory particularly haunting is that there would be no advance warning whatsoever, as the expanding bubble boundary would represent the absolute edge of a new physical law, and anything caught within its expanding sphere would be fundamentally restructured according to these new physics, meaning that atoms, particles, and all the forces that hold matter together could transform into entirely different configurations or cease to function in ways we recognize. The true vacuum bubble would expand relentlessly, consuming entire galaxies and stellar systems, rewriting the constants of nature itself, and rendering all life and consciousness instantaneously extinct without anyone ever knowing what happened, as the very nature of reality would transform before any signal carrying information about the catastrophe could propagate outward. Imagine a molecular scissors that can find a single sentence within the 3 billion letter instruction manual that is your DNA, locate the exact misspelling, and correct it with surgical precision, and you begin to grasp the revolutionary nature of CRISPR gene editing technology. This breakthrough emerged from an unexpected place, discovered in the immune systems of bacteria that use this molecular mechanism as a defense against invading viruses, a natural mechanism refined over millions of years of evolutionary arms race between bacteria and the pathogens that threaten them. When scientists recognized that this ancient bacterial defense system could be repurposed and adapted to edit human genes with remarkable accuracy and efficiency, they unlocked a capability that seemed to exist only in the realm of science fiction just decades earlier. The mechanism works through an elegant simplicity that belies its profound implications. A guide molecule directs the CRISPR protein to the exact location in the genome where an edit is needed. The protein cuts both strands of the DNA helix at that precise spot, and then the cell's natural repair mechanisms either delete the problematic section or allow scientists to insert new genetic material into the break. What makes CRISPR fundamentally different from previous gene editing technologies is its remarkable affordability, accessibility, and ease of use compared to earlier methods that required specialized equipment and years of training to operate effectively. The implications seem limitless, correcting genetic mutations responsible for sickle cell disease, cystic fibrosis, and certain forms of hereditary blindness, enhancing immune cells to fight cancer more effectively, potentially eliminating hereditary diseases before they manifest in future generations. Yet despite these extraordinary capabilities, we have normalized the existence of this technology with surprising psychological ease, treating it as simply another medical innovation rather than grappling with the profound philosophical questions it raises about our relationship with human nature itself. We discuss genetic editing in clinical terms, while the deeper implications about designer babies, genetic inequality, and the potential creation of genetic underclasses remain largely unexamined in mainstream consciousness, suggesting a remarkable capacity for humans to accept transformative technologies without fully processing their existential significance. Deep within the cellular machinery of every living human being exists a small, oval-shaped organelle called the mitochondrion, and within it resides a genetic blueprint that tells us an extraordinary story about our collective ancestry. This story begins with the discovery that mitochondria contain their own DNA, separate and distinct from the DNA housed in the nucleus of the cell. And this mitochondrial DNA is inherited exclusively through the maternal line, passed down from mother to child across countless generations with remarkably few mutations along the way. Scientists realized that if they traced this maternal genetic inheritance backward through time, following the maternal lineages of all living humans, they would eventually converge at a single woman who lived somewhere between 150,000 and 200,000 years ago in Africa. This ancestral woman, whom researchers named Mitochondrial Eve, was not the first human or the only human alive during her time, but she was the only woman in that entire era whose unbroken line of female descendants survives to the present day. Every other woman from her time period either had no daughters or had daughters whose own female lineages eventually produced no female offspring, causing those branches of the family tree to disappear from the genetic record like paths that simply ended. The mechanism behind this phenomenon involves the mathematical inevitability of inheritance combined with the random nature of reproduction patterns. When a woman has only sons, her mitochondrial DNA cannot pass forward to future generations, and when a woman has daughters who themselves have only sons, that same genetic line terminates there as well. Over thousands of years, with millions of women reproducing and dying, producing sons and daughters in unpredictable patterns, most maternal lineages gradually died out through nothing more than statistical chance. The female line that did survive did so not because that woman was exceptional or lived longer or had more children than others, but simply because, through the pure randomness of human reproduction, her descendants happened to always include at least one daughter in each generation, and those daughters had daughters, and so on, right up until today. Deep within the genetic code of every man alive today exists a thread of DNA that connects him to a single ancestor who lived somewhere between 50,000 and 200,000 years ago, a man we have never seen and whose name we will never know, yet whose Y chromosome has been passed down through an unbroken chain of male descendants across countless generations, and this remarkable ancestor has come to be known as Y-Chromosomal Adam. Representing not the earliest human male ever to exist, but rather the most recent male from whom all living men are descended through an exclusively patrilineal line. The Y chromosome is unique among our genetic material because it is passed almost entirely unchanged from father to son, with only rare mutations occurring as it travels through the generations, which means that by studying the variations and mutations present in the Y chromosomes of men around the world today, geneticists can work backwards through time like detectives following a trail of clues. Calculating how long ago these mutations must have first occurred, and thereby pinpointing when a common ancestor carrying the original unmutated Y chromosome must have lived and reproduced. What makes Y-chromosomal Adam conceptually fascinating is the realization that this ancient man was not isolated or unique in his time, as he lived in a world populated by thousands or even millions of other humans, including many other males who were his contemporaries. Yet somehow only his direct male line survived intact through all the eons that followed, while all other male lineages eventually ended, either through chance events, reproductive bad luck, or the simple vagaries of history that determine which bloodlines persist and which fade away into extinction. The mechanism behind this inheritance pattern is fundamentally about probability and time, for in any population, some family lines will by random chance produce more surviving sons than others, and over thousands of years, these small statistical advantages compound and multiply, eventually resulting in one lineage coming to represent the ancestry of an entire population. Much like how a single tree in a forest might come to dominate the landscape not necessarily because it was stronger or better, but simply because circumstances aligned so that its seeds took root more successfully and its branches spread more widely than its competitors. Imagine standing in a museum gazing upon fragments of corroded bronze, so encrusted with the patina of 2,000 years that they barely resemble anything recognizable as a device. Yet contained within these oxidized pieces lies what may be humanity's most perplexing technological artifact, a mechanism of such sophisticated engineering that its very existence challenges everything we thought we understood about ancient Greek civilization and the trajectory of human technological progress. In the year 1900, sponge divers working off the Greek island of Antikythera discovered a Roman shipwreck resting on the seafloor, and among the treasures and sculptures they recovered were these small bronze fragments, initially dismissed as merely decorative pieces or remnants of some unknown religious object. Yet when scientists began to examine them more carefully, particularly after modern imaging techniques like X-ray and three-dimensional scanning became available in recent decades, they realized they were looking at something altogether extraordinary, an ancient analog computer, a device containing at least 30 interlocking gears of astonishing precision, designed to predict the positions of celestial bodies with remarkable accuracy. The mechanism appears to have been constructed around the 1st century before Christ, a time when such technology should not have existed according to our conventional understanding of ancient manufacturing capabilities, and it functioned as an orrery, an instrument that mechanically demonstrated the movements of the sun, moon, and planets across the sky, allowing astronomers and philosophers to understand the cosmos through the rotation of its gears and the resulting indicator hands that would point to specific positions and dates. What makes this discovery psychologically disorienting is the simple fact that nothing comparable appears in the archaeological record again until the emergence of mechanical clocks in medieval Europe, nearly 1,000 years later, suggesting either that the ancients possessed technological knowledge that was somehow lost and forgotten, or that such devices were extraordinarily rare and precious, perhaps unique to a single brilliant inventor whose work never found replication among his contemporaries. Nestled in the limestone hills of southeastern Turkey, approximately 9 miles from the Syrian border, lies an archaeological site that fundamentally challenges everything we thought we understood about human civilization and the development of complex societies, a place called Göbekli Tepe, which translates from Turkish to mean Potbelly Hill. And what researchers have discovered there over the past 2 decades has quietly revolutionized our understanding of prehistoric human behavior and social organization in ways that continue to ripple through academic circles with profound implications. The site itself dates back to approximately 9,500 BCE, making it roughly 7,000 years older than the Egyptian pyramids and predating Stonehenge by some 6,500 years. Yet what makes this discovery truly extraordinary is not merely its age, but rather what the ruins reveal about who built them and why, for at Göbekli Tepe we find massive T-shaped stone pillars, some reaching heights of 18 feet and weighing up to 16 tons. Arranged in oval and circular configurations, decorated with intricate carvings of foxes, boars, snakes, and scorpions, suggesting a level of artistic sophistication and coordinated labor that should not have existed in what archaeologists had always assumed was a pre-agricultural, hunter-gatherer society. The logical mechanism that makes this discovery so psychologically disorienting is that for generations, our academic understanding had established a clear narrative progression through human development. First came nomadic hunting and gathering, then agriculture emerged, and only after agriculture could societies accumulate enough surplus resources to support specialized craftspeople, organized religion, and monumental construction. Yet Göbekli Tepe appears to reverse this sequence entirely, suggesting instead that monumental ritual sites and complex social organization may have actually preceded agriculture rather than followed it, implying that the psychological and social drive to gather, to create religious meaning, and to build together was so fundamental to human nature that it motivated people to organize themselves in ways previously thought impossible without agricultural surplus. Deep within Yale University's Voynich Rare Book and Manuscript Library exists one of history's most perplexing artifacts, a bound vellum codex known as the Voynich Manuscript, which measures roughly 6 by 9 inches and contains approximately 240 pages filled entirely with an undeciphered script, accompanied by elaborate botanical and astronomical illustrations rendered in soft watercolor pigments that have faded only slightly across the centuries. The manuscript first surfaced in the historical record in the early 1600s when it appeared in the collection of Holy Roman Emperor Rudolph II, a man known for his obsessive accumulation of rarities and curiosities, and it subsequently passed through the hands of various collectors and scholars until 1912, when an American antiquarian book dealer named Wilfrid Voynich acquired it from a Jesuit college in Rome, thus giving the mysterious volume the name by which it is now universally known, though even this seemingly simple transaction raises questions about provenance and authenticity that remain unresolved to the present day. The text itself consists of a writing system, unlike anything scholars have encountered in their studies of human linguistic evolution, composed of approximately 30 to 40 distinct glyphs that form words of varying length, arranged in neat lines across pages with occasional marginal notations and corrections that suggest a deliberate act of composition rather than random marking or deliberate obfuscation. Yet every attempt to decode this script through linguistic analysis, cryptographic methods, computer modeling, and artificial intelligence has ultimately failed to produce any convincing translation or even definitive proof that the manuscript represents an actual language rather than elaborate nonsense or an idiosyncratic personal code. The illustrations within its pages depict plants that do not correspond to any known species, elaborate cosmological diagrams with undeciphered labels, nude female figures engaged in unknown activities within complex chamber systems, astronomical charts showing celestial bodies and zodiacal signs, and bathing scenes that suggest the manuscript may have been intended as some form of medicinal or botanical reference guide. Though the complete absence of any recognizable content prevents scholars from determining its actual purpose with certainty. In the year 2007, scientists launched a spacecraft carrying a peculiar payload of microscopic organisms called tardigrades, also known as water bears, into the vacuum of space itself, and what they discovered fundamentally challenged our understanding of what life itself could endure and survive under the most extreme conditions imaginable. These creatures, which are only about half a millimeter in length, were exposed to the absolute vacuum of low Earth orbit, subjected to intense cosmic radiation, extreme temperature fluctuations ranging from near absolute zero to blistering heat, and conditions that would instantaneously kill virtually every other known organism on Earth. Yet remarkably, when the spacecraft returned and researchers examined the tardigrades, they found that many of them had survived this ordeal entirely intact and unharmed. The mechanism behind this extraordinary survival capability lies in a unique biological process that tardigrades can enter called cryptobiosis, which is essentially a state of suspended animation where the creature's metabolism drops to an undetectable level, their body moisture content decreases dramatically, and they essentially transform into a desiccated husk that can remain in this dormant state indefinitely until conditions become favorable again for reanimation. During this cryptobiotic state, the tardigrade cells produce special protective molecules called trehalose, which acts like a molecular cushion protecting the delicate structures within the cell from damage, while simultaneously the creature's DNA becomes wrapped in protective proteins that shield it from the devastating effects of cosmic radiation that would normally shred the genetic material of any living organism. What makes this even more remarkable is that tardigrades seem to possess this capability not because they evolved in space, which would be absurd, but rather because they evolved on Earth in the most inhospitable terrestrial environments imaginable, such as the moss of Antarctic mountains, the depths of ocean trenches, and the boiling waters of thermal vents, where they encountered conditions so harsh that developing the ability to enter cryptobiosis became not just an advantage, but an absolute necessity for survival. Consider the remarkable phenomenon of avian migration, where billions of birds traverse thousands of miles across continents and oceans with a precision that defies conventional biological explanation, navigating routes their species has traveled for millennia through mechanisms that modern science has only recently begun to understand. For decades, ornithologists observed that migratory birds possessed an uncanny ability to maintain their heading even on overcast days when the sun and stars were completely obscured, suggesting that they relied upon something far more subtle than visual navigation alone. Research conducted over the past 2 decades has revealed that many bird species, particularly warblers and robins, appear to possess an internal magnetic compass that operates not through the detection of the Earth's magnetic field by conventional means, but through quantum mechanical processes occurring within specialized proteins located in the bird's eyes. Within these photoreceptor cells exists a protein called cryptochrome, and when light enters the eye, It causes electrons within this protein to become entangled in a quantum state, meaning the electrons exist in multiple states simultaneously until measured or observed. This quantum entanglement creates what physicists call a radical pair, two unpaired electrons whose quantum states remain mysteriously connected across tiny molecular distances. And remarkably, these entangled particles appear to respond to the precise orientation of Earth's magnetic field in ways that classical physics cannot fully explain. The bird's brain then interprets the subtle shifts in these quantum states as directional information, essentially using quantum mechanics as a biological navigation system. What makes this phenomenon truly extraordinary is how it persists despite seeming to violate our understanding of how quantum effects should behave in the warm, wet environment of a living cell, where quantum coherence typically collapses almost instantaneously. Yet somehow, evolution has engineered a biological system that maintains quantum entanglement long enough to extract meaningful navigational information, creating a bridge between the quantum realm that governs subatomic particles and the macroscopic world of living creatures navigating across continents. Deep within the chloroplasts of plant cells, where sunlight begins its transformation into the chemical energy that sustains nearly all life on Earth, something extraordinary happens that challenges our fundamental understanding of how biology operates at its most basic level. When a photon of light strikes a chlorophyll molecule, it excites an electron to a higher energy state, and this electron must then travel through a series of protein complexes in what we might expect to be a straightforward journey from one location to another, following the classical laws of physics that govern the everyday world around us. Yet what researchers have discovered over the past 2 decades is that this electron does not simply take one path through these protein structures. Instead, it appears to simultaneously explore multiple routes at once, a phenomenon that belongs not to the realm of classical physics, but to the strange and counterintuitive world of quantum mechanics, where particles can exist in multiple states until they are observed. This quantum effect, known as quantum coherence or quantum superposition, allows the electron to sample all available pathways through the photosynthetic machinery and essentially find the most efficient route with nearly perfect accuracy, achieving energy transfer efficiency rates that hover around 95%, which would be virtually impossible to achieve if the electron were constrained to move along a single classical trajectory. The mechanisms underlying this phenomenon involve the electron maintaining what physicists call a coherent quantum state as it travels through the light-harvesting complexes, where the vibrational patterns of the surrounding protein environment actually seem to protect this delicate quantum coherence rather than destroying it, which was entirely unexpected because quantum effects typically dissolve almost instantly when exposed to warm, wet biological environments. The persistence of quantum effects in photosynthesis suggests that over billions of years of evolution, plants have somehow learned to harness and preserve quantum mechanical phenomena within their cellular machinery, creating biological structures that operate with an efficiency that bridges the gap between the quantum and classical worlds in ways we are only beginning to understand and replicate in our technological applications. Within your body right now exists an entire invisible civilization of microorganisms that outnumber your own cells, and despite spending your entire life hosting these creatures, you likely give them almost no conscious thought at all. Deep within your digestive tract, across the surface of your skin, within your mouth and nasal passages, and in countless other environments throughout your body, trillions upon trillions of bacteria, fungi, viruses, and other microscopic life forms have established themselves as permanent residents, forming what scientists call the human microbiome. These organisms are not invaders or parasites in the traditional sense, but rather essential partners in a relationship so fundamental that your survival as a human being depends entirely on their presence and their continuing cooperation with your body's own biological systems. Your gut microbiome alone contains roughly the same number of microbial cells as you have human cells, meaning you are quite literally half microorganism by cell count. Yet when you look in the mirror, you see only yourself, never acknowledging the vast metabolic city that dwells within. The mechanisms by which these microbes influence your health are astonishingly complex and far-reaching, affecting everything from your immune system's ability to recognize and fight genuine threats, to your mental health through the production of neurotransmitters that communicate directly with your brain via the vagus nerve, to your metabolism and weight regulation, to your susceptibility to chronic diseases. These microbial communities produce essential vitamins that your own cells cannot manufacture, break down complex carbohydrates that you would otherwise be unable to digest, train your immune system by exposing it to harmless and beneficial microbes so it doesn't overreact to genuine dangers, and produce compounds that protect your intestinal lining from invasion by actual pathogens. Yet despite this extraordinary interdependence, and the fact that we have known about the microbiome in some form for over a century, most people continue through their lives in a state of profound ignorance about this microscopic reality, taking antibiotics that devastate these communities without replacing them, consuming diets that starve beneficial microbes while feeding harmful ones, and generally treating their bodies as if they were single-organism entities rather than complex ecosystems. Imagine sitting in a theater watching a film, and suddenly on screen, a character bites into a lemon, their face contorting as the sour juice floods their mouth, and in that exact moment you feel your own jaw tighten and your mouth water in response to something you are not actually tasting. Or consider watching a friend stub their toe on a table leg, and before they even cry out, you find yourself wincing, feeling a phantom pain in your own foot as though the injury were somehow transferred through your vision alone. These are not mere coincidences or imaginative flights of fancy, but rather the result of a remarkable neural system that was only discovered in the 1990s when Italian neuroscientists were conducting experiments on macaque monkeys. They had electrodes implanted in the brains of these primates to study motor neurons, cells that fire when an animal performs a specific action, but they made an astonishing discovery when they noticed that certain neurons would activate not only when the monkey performed an action, but also when the monkey simply observed another monkey or a human performing that exact same action. These neurons were named mirror neurons, and they essentially allow our brains to simulate the actions and experiences of others by internally mimicking them, creating a neural bridge between observation and action that had previously been invisible to science. The mechanism underlying mirror neurons is deceptively elegant yet profoundly complex, operating as a kind of neural simulation system that maps external behaviors onto our own motor and sensory systems. When you watch someone reach for a cup, your mirror neuron system activates the same neural pathways that would fire if you yourself were reaching for that cup, creating a kind of internal echo of their movement. This neural mirroring extends beyond simple motor actions into the realm of emotion and sensation, which is why watching someone experience pain creates activity in the pain centers of your own brain, and observing someone's joy activates your own reward systems. Scientists believe that this system evolved as a mechanism for understanding others' intentions and mental states, allowing us to predict what someone might do next based on what we observe them doing, and this predictive capability would have provided enormous survival advantages in social species that depend on quick and accurate interpretation of others' behaviors and emotions. For most of human history, scientists believed that the adult brain was essentially fixed and unchangeable, a biological machine that lost neurons over time and could never rewire itself or form new neural pathways once development had concluded in early adulthood. This notion was so deeply entrenched in neuroscience that it became the foundational assumption upon which entire fields of medicine and psychology were built, creating a pessimistic view of human potential and recovery after brain injury or disease. However, beginning in the latter half of the 20th century, researchers began discovering something remarkable that fundamentally challenged this understanding, namely that the adult brain possesses an extraordinary capacity called neuroplasticity, which is the ability to physically reorganize itself by forming new neural connections throughout life, allowing the brain to compensate for injury, adapt to new experiences, and create new pathways even well into old age. When someone learns a musical instrument, their auditory cortex and motor cortex begin to physically change shape and size, with brain imaging studies showing measurable increases in gray matter volume in regions dedicated to processing sound and executing finger movements, changes that correlate directly with hours of practice and level of skill. Similarly, when individuals recover from strokes that have damaged specific brain regions, other areas of the brain can be recruited and retrained to take over the functions previously handled by the injured tissue, demonstrating that the brain is far more fluid and adaptable than the static model suggested. The mechanism underlying neuroplasticity involves the strengthening and weakening of synaptic connections between neurons based on activity and experience, a principle captured in the phrase that neurons which fire together wire together, meaning that repeated activation of neural circuits causes the connections between those neurons to become stronger and more efficient, while unused connections gradually weaken and fade away. London taxi drivers who spend years memorizing the city's labyrinthine street layouts develop enlarged hippocampi, the brain region crucial for spatial memory, illustrating how intensive experience literally reshapes brain anatomy, while individuals who learn new languages show increased connectivity between language processing areas, demonstrating how intentional mental effort produces physical neural reorganization. Consider the moment you finish a task and your mind seems to drift into a kind of purposeless wandering, where thoughts about yourself, your past, your future, and your relationships begin to cascade through your consciousness without any deliberate direction or control. And you realize that even though you are not actively focusing on anything external, your brain is remarkably active and engaged in this self-referential thinking. This phenomenon, which neuroscientists discovered through functional magnetic resonance imaging scans, revealed an intricate network of brain regions that activate when you are not concentrating on the outside world, a system they named the default mode network. And this discovery fundamentally changed how we understand the nature of consciousness and mental activity. The default mode network includes regions such as the medial prefrontal cortex, the posterior cingulate cortex, and the angular gyrus, and these areas work together in a coordinated symphony of neural firing that becomes most prominent during moments of rest, daydreaming, or mind-wandering, while simultaneously becoming suppressed when you direct your attention to external tasks. What makes this discovery so philosophically profound is that it demonstrates your brain is never truly idle, that the notion of a resting mind is essentially illusory, and that vast computational resources are constantly devoted to introspection, autobiographical memory, theory of mind, and social reasoning. The default mode network appears to serve critical functions in maintaining your sense of self, constructing narratives about your life, anticipating future scenarios, and imagining the mental states of others. Yet despite understanding these functions, we continue to speak of mind-wandering as wasteful, of daydreaming as a form of mental laziness, and of resting as doing nothing, when in reality your brain is engaged in some of its most creative and self-focused work during these supposedly inactive periods. The irony deepens when you consider that meditation practices, which explicitly teach you to reduce default mode network activity, often create a sense of well-being and reduced rumination, suggesting that perhaps our constant self-referential thinking, our endless replaying of social interactions, our persistent worry about the future, and our obsessive reviewing of the past may not always serve us well despite being fundamental to how our minds naturally operate when left to their own devices. Imagine a patient lying on an operating table, and surgeons are about to perform one of the most philosophically unsettling procedures in medical history, severing the corpus callosum, that thick bundle of approximately 200 million nerve fibers that connects the left and right hemispheres of the brain and allows them to communicate with one another. These split brain experiments, which began in earnest during the 1960s with neuroscientist Roger Sperry and his colleagues, were originally designed to help epilepsy patients by preventing seizures from spreading between hemispheres. Yet what researchers discovered in the aftermath of these procedures fundamentally challenged our understanding of consciousness, identity, and what it means to be a unified self. When the connection between hemispheres was severed, something remarkable and deeply unsettling occurred, and researchers found that each hemisphere could operate independently, perceiving different information, processing different thoughts, and seemingly making different decisions, all within a single skull, a single body, a single person who had always believed themselves to be one unified consciousness. In the classic experimental setup, researchers would present visual information exclusively to one hemisphere by using a special apparatus that flashed images to either the left or right visual field of a patient's eyes, ensuring that only one hemisphere received the information while the other remained unaware, and what they discovered was extraordinary. The left hemisphere could describe what it saw and articulate its thoughts with words, while the right hemisphere could demonstrate knowledge of the image through pointing or nonverbal responses. Yet the two hemispheres might have completely different interpretations, emotional reactions, or even contradictory intentions about the same stimulus. The mechanism underlying these phenomena relates to the lateralization of brain function, where the left hemisphere typically dominates language and analytical processing, while the right hemisphere specializes in spatial awareness, emotional processing, and holistic thinking. And when their communication is severed, these specialized systems become isolated islands of consciousness that cannot share information or coordinate their responses. Imagine waking up after an amputation, reaching for your alarm clock with a hand that no longer exists, or feeling an unbearable itch on a foot that was surgically removed months ago. This is the reality of phantom limb syndrome, a condition affecting the vast majority of amputees who report ongoing sensations from their missing limbs, sensations so vivid and persistent that they can feel pain, temperature, texture, and even movement in body parts that are no longer physically present. A person might feel their phantom fingers curling, their phantom toes pressing against phantom ground, or their phantom arm reaching across a phantom table with such clarity that the distinction between what is real and what is remembered becomes almost meaningless. Some amputees describe their phantom limbs as perfectly intact, while others report them as contorted, twisted at impossible angles, or frozen in the exact position they held at the moment of amputation. The pain can be excruciating, described as cramping, burning, stabbing, or electric, and it can persist for decades after the actual limb has been lost, seemingly indifferent to the fact that there is nothing there to hurt. The mechanism behind this phenomenon reveals itself when we examine how the brain creates the body map, a neurological representation of where all your body parts exist in space and how they should behave. This map was established over your entire lifetime as your brain received constant feedback from your limbs through countless nerve endings and sensory receptors, creating an intricate neural network that knows exactly where your hand should be and what it should feel like to move your fingers. When amputation severs the physical connection, it does not erase this deeply embedded neural map. The brain continues sending signals to the missing limb because the neural pathways remain intact, and when there is no feedback coming back, the brain essentially becomes confused, continuing to perceive and sometimes even feel sensations from a limb that is not sending any actual information. The phantom limb essentially exists in the space between physical reality and neural memory, a ghost limb written into the architecture of your nervous system. What makes phantom limb syndrome so profoundly strange is how it persists despite our complete intellectual understanding that the limb is gone. Imagine a patient who has suffered damage to the visual cortex, the region of the brain responsible for conscious visual perception, yet when researchers place objects in their blind field and ask them to guess their location or orientation, they perform far better than random chance would predict, all while maintaining genuine conviction that they cannot actually see anything at all. This peculiar neurological condition, known as blindsight, presents one of the most perplexing paradoxes in neuroscience, challenging our fundamental understanding of what it means to see and what constitutes conscious awareness. The patients themselves experience a complete absence of visual sensation in the damaged region of their visual field, describing it as a blank space or void, yet their hands and bodies respond to visual stimuli that their conscious minds insist they cannot perceive. When asked to reach toward an object in their blind field, they will navigate around obstacles with remarkable accuracy, or they will catch a moving ball that they claim to have no awareness of whatsoever. The mechanism underlying this strange dissociation appears to involve intact pathways that bypass the primary visual cortex entirely, routing visual information through older, evolutionarily ancient structures in the brain, such as the superior colliculus and other subcortical regions that process motion, location, and basic visual features without requiring conscious awareness. These alternative neural routes seem to preserve certain visual functions, while the conscious, reportable experience of vision remains completely absent, suggesting that our brains possess multiple independent systems for processing visual information, many of which operate entirely outside the realm of consciousness. What makes blindsight particularly mind-bending is not merely the dissociation itself, but rather how it demolishes the intuitive notion that seeing and knowing are the same thing, that perception and consciousness are inevitably linked. The phenomenon reveals that the brain can extract meaningful information from the visual world, generate appropriate behavioral responses, and guide complex motor actions without any corresponding conscious experience or subjective awareness. Yet despite the remarkable implications of blindsight for our understanding of consciousness itself, despite decades of research demonstrating its existence across numerous patients, we continue to operate under the largely unexamined assumption that consciousness and perception must naturally accompany one another, that to process information is necessarily to experience it. Imagine sitting across from someone who is speaking directly to you, and as you watch their lips move while listening to the sound of their voice, you become absolutely certain of what word they have just spoken to you, only to discover moments later that what you actually heard was something entirely different from what their lips were clearly articulating in front of your eyes. This is the McGurk Effect, a remarkable phenomenon that demonstrates the profound disconnect between what our eyes see and what our ears hear, revealing that our perception of speech is not a simple matter of listening, but rather a complex negotiation between visual and auditory information that our brain conducts entirely without our conscious awareness or permission. When psychologists Harry McGurk and John MacDonald first documented this effect in 1976, they were studying how infants develop speech perception, and they discovered something that would challenge our most basic assumptions about how we understand the world around us. In their classic experiment, they created a video in which a person's lips were clearly articulating the syllable ga ga ga, but the audio track they overlaid onto this video contained the sound ba ba ba, and when viewers watched this video with both sound and image, they overwhelmingly reported hearing da da da, a syllable that existed in neither the visual nor the audio information provided to them. Instead, their brains had unconsciously merged the two sources of information together, creating an entirely new perception that was neither what they saw nor what they heard. The mechanism behind this effect lies in the remarkable way our brains process multisensory information, treating vision and hearing not as separate channels that should be combined like simple addition, but rather as complementary sources of data that must be integrated and reconciled at a fundamental neurological level. When you watch someone speak, your visual cortex is processing the movements of their lips, jaw, and tongue, extracting patterns about which sounds should logically follow from these movements based on years of experience and learning, while simultaneously your auditory cortex is processing the acoustic information arriving through your ears. And these two streams of information are not processed separately in different parts of your brain, but rather converge in areas responsible for speech perception, where they are weighted and integrated together in real time. Imagine a world where the boundaries between your senses have dissolved into something far more fluid and interconnected than what most people experience, where hearing a particular musical note doesn't just produce sound, but simultaneously fills your visual field with a specific color, or where tasting a meal instantly creates geometric patterns in your mind's eye that you can perceive as vividly as if they were painted in the air before you. This is the reality for individuals with synesthesia, a neurological condition where the stimulation of one sensory pathway leads to automatic and involuntary experiences in a completely different sensory pathway. And what makes this phenomenon so genuinely fascinating is that these cross-sensory associations are not learned or cultivated through any conscious effort, but rather appear to be hardwired into the architecture of the brain itself from birth or early development. When a person with grapheme color synesthesia looks at the number 3, they don't think about the color red and then associate it mentally. Instead, the color red appears to be an inherent property of that number, as automatic and unavoidable as the shape of the numeral itself, and this happens consistently across time, with the same number always producing the same color without variation. Neuroimaging studies have revealed that synesthesia emerges from increased neural connectivity between sensory regions that typically remain somewhat segregated in non-synesthetic brains, suggesting that in synesthetic individuals, the pathways between areas responsible for processing different sensory inputs remain partially fused or fail to fully prune back during development when most children's brains undergo this normal refinement process. The mechanism appears to involve both genetic factors and subtle differences in how connections form during critical periods of brain development, with evidence suggesting that some people may possess a natural genetic predisposition toward enhanced cross-sensory connections that, when expressed, creates these remarkable bridges between different sensory domains. For decades, lucid dreaming existed in a peculiar liminal space between subjective experience and scientific impossibility, dismissed by mainstream sleep researchers as nothing more than wishful thinking or false memory, yet documented by countless individuals who claim to possess the remarkable ability to recognize they were dreaming while still asleep and subsequently exert conscious control over the dream environment. The turning point came in the 1980s and 90s when sleep researchers conducted ingenious experiments where lucid dreamers were instructed to perform predetermined eye movements at specific moments they predicted they would achieve lucidity. And remarkably, when monitored in sleep laboratories with electrodes measuring rapid eye movement sleep. These eye movements appeared in the actual recorded data at precisely the predicted times, demonstrating an undeniable link between conscious intention and measurable physiological responses during REM sleep. This breakthrough established that lucid dreaming was not mere imagination or false recollection, but rather a verifiable state of consciousness where the dreamer maintains awareness and agency while their brain exhibits the neurological patterns of genuine sleep, creating what researchers termed a hybrid state of consciousness that exists between the objective reality of sleep and the subjective awareness of wakefulness. Subsequent neuroscience investigations revealed that during lucid dreams, activity in the frontal and prefrontal cortex, regions responsible for metacognition and self-awareness, remained elevated compared to non-lucid REM sleep, explaining how the brain could simultaneously experience the vivid hallucinations of a dream while maintaining the reflective capability to recognize the dream as such. Yet despite this compelling scientific validation and the reproducibility of these findings across multiple independent laboratories worldwide, lucid dreaming remains remarkably absent from mainstream scientific discourse and public consciousness, rarely taught in educational systems, largely absent from popular culture conversations about dreams and consciousness, and sometimes still questioned by sleep specialists who were trained when the phenomenon was universally rejected as impossible. Imagine waking in the dead of night, your consciousness suddenly snapping into awareness, only to discover that your body remains completely frozen beneath you, unresponsive to even the most desperate mental commands, while your mind races with a clarity and intensity that feels almost supernatural in its vividness. This is the experience of sleep paralysis, a phenomenon that has haunted human sleep for millennia, described across cultures with remarkably similar language involving demons, shadows, and malevolent presences sitting upon the chest of the helpless sleeper. The person lies there fully aware, eyes perhaps slightly able to move in their sockets, heart pounding rapidly, breathing becoming shallow and difficult, and the overwhelming sensation that something profoundly wrong is occurring in that dark bedroom. Yet when the episode passes minutes later, the body suddenly releases and normalcy returns as if nothing happened at all. What science has discovered is that sleep paralysis is actually the result of a profound mismatch between two normally synchronized biological systems, occurring when the brain transitions between sleep stages in an unusual sequence. During rapid eye movement sleep, the stage where most vivid dreams occur, your brain deliberately paralyses your voluntary muscles to prevent you from acting out your dreams and potentially harming yourself or others. A protective mechanism so complete that only your eyes and diaphragm remain operational. When sleep paralysis occurs, consciousness awakens from REM sleep while the motor paralysis remains fully engaged, creating the surreal and terrifying experience of being mentally awake while physically locked inside an unresponsive body. The brain, still partially in dream mode and flooded with the neurochemistry of sleep, often generates hallucinations during this threshold state, producing the sensation of a presence in the room, a weight upon the chest, or shadowy figures at the periphery of vision, experiences so consistent across human populations that ancient cultures attributed them to demons and contemporary folklore maintains them as supernatural encounters. When you wake from a vivid dream in which you were falling from a building or being chased through an endless hallway, there is an almost irresistible urge to assign meaning to it, to consult dream interpretation guides or confide in someone who might decode the symbols your sleeping mind has woven together. Yet the neuroscience of dreaming reveals a far more mechanical and less prophetic process occurring in your brain during these nocturnal experiences. During the rapid eye movement phase of sleep, your brain enters a state of heightened neural activity in certain regions while simultaneously becoming disconnected from the logical analytical structures that normally govern your waking consciousness. And this peculiar neurochemical state creates the conditions for the construction of these elaborate, often bizarre narratives that feel deeply significant and emotionally resonant at the time of the dream. The prefrontal cortex, the region responsible for logical reasoning and critical evaluation, becomes significantly less active during REM sleep, while the limbic system, including the amygdala which processes emotions and the hippocampus which handles memory formation, becomes more activated, leading to dreams that are emotionally intense but logically inconsistent, featuring impossible scenarios and rapid scene transitions that would seem absurd in the waking state. Neuroscientists and sleep researchers have come to understand that dreams are essentially the brain's attempt to make narrative sense of the random neural firing patterns that occur during REM sleep, a process sometimes called the activation synthesis hypothesis, wherein your brain generates stories to explain the chaotic electrical activity happening throughout its various regions. Much like a person waking in darkness might construct an elaborate explanation for a mysterious sound that was simply the house settling. Yet despite possessing this neurological understanding, the human impulse to interpret dreams as meaningful messages persists across cultures and throughout history, with people continuing to believe that dreams about water represent emotions, snakes represent danger or transformation, and deceased relatives represent unfinished business. Even though the actual mechanisms generating these dreams involve nothing more mystical than neurotransmitter fluctuations and random neural activation, patterns that the conscious mind is attempting to organize into coherent form. Imagine living in a world where the voices inside your head were not your own thoughts, but divine commands from God speaking directly to you, guiding your every action and decision with absolute authority. This was the reality for ancient human civilizations, according to psychologist Julian Jaynes and his revolutionary bicameral mind theory, which proposes that the human mind did not always operate as a unified, self-aware consciousness the way we experience it today. Instead, Jaynes suggested that until relatively recently in human history, roughly 3,000 years ago, the human brain was actually divided into two distinct chambers or hemispheres with separate functions, where one side generated language and issued commands, while the other side received and obeyed those commands without question or conscious deliberation. The left hemisphere, typically associated with language and analytical processing, would generate what we now call internal monologue, but in ancient humans, this would have been experienced as an external voice, authoritative and unmistakably non-self, commanding the right hemisphere to act. Archaeological evidence and ancient texts support this theory in surprising ways, as we find that ancient Sumerian, Egyptian, and Hebrew texts are filled with accounts of people hearing voices from gods, receiving divine instruction through internal audio, and following commands without the sense of personal agency or questioning that modern humans would immediately employ. The mechanism behind this theory suggests that consciousness as we know it, with its unified sense of self and free will, is actually a relatively recent evolutionary development, emerging only as the bicameral mind gradually integrated and collapsed into the unified consciousness we now possess, a process that accelerated during periods of cognitive and cultural upheaval. What makes this theory particularly fascinating is how it explains not only ancient religious experiences, but also modern phenomena like auditory hallucinations in schizophrenia, the persistence of hearing voices reported by people in altered mental states, and even the universal human experience of having thoughts that sometimes feel like they arrive unbidden from outside ourselves. Despite the elegance and explanatory power of Jaynes' theory, the scientific community has largely moved toward more cautious interpretations, acknowledging that while consciousness and self-awareness have certainly evolved and changed throughout human history, the exact mechanism and timeline proposed by Jaynes remains speculative and difficult to definitively prove. Consider the octopus, a creature that exists in the ocean depths with a nervous system organized in a way that fundamentally challenges everything we thought we understood about the nature of consciousness and distributed intelligence. The octopus possesses approximately 500 million neurons, which is remarkable for an invertebrate, but what makes this even more extraordinary is that 2/3 of these neurons are not located in its brain, but rather distributed throughout its 8 arms, creating a neural architecture that is fundamentally alien compared to the centralized nervous systems of vertebrates like ourselves. When an octopus arm encounters an object in the darkness of the seafloor, that arm can identify the texture, taste, and chemical composition of the object, process this information locally, and decide upon an action independently, all without necessarily reporting back to the central brain for approval or guidance. The arm can reach out, explore, manipulate, taste, and even reject food items, demonstrating what appears to be autonomous decision-making capacity at the limb level. Scientists have observed octopuses engaging in behaviors that suggest not only problem-solving intelligence, but also what might be called personality, stubbornness, and even playfulness, as individual octopuses develop distinct preferences for different types of food, show varying levels of curiosity when presented with novel objects, and appear to recognize individual human researchers who have interacted with them before. The question that emerges from studying these creatures is whether consciousness requires a unified central processor, whether it can exist in a distributed and decentralized form, and what it even means for a being to be conscious when different parts of its body seem to possess their own form of decision-making capacity. We have long assumed that consciousness is something that emanates from a brain, something unified and singular and centralized, yet the octopus suggests that intelligence, awareness, and intentional behavior might arise from systems that are far more alien and dispersed than we ever imagined, reminding us that consciousness itself may be far stranger and more varied in its expressions than our human-centric theories have previously allowed. When researchers first observed crows in the forests of New Caledonia, they witnessed something that would fundamentally challenge our understanding of animal cognition and tool use in the natural world. These remarkable birds were selecting twigs and leaves with deliberate precision, modifying them into specific shapes, and then using these crafted instruments to extract insects from deep within tree bark and hidden crevices that their beaks alone could never reach. What made this discovery truly extraordinary was not simply that crows used tools, as some animals do, but rather that they demonstrated an almost artistic level of sophistication in designing and refining these implements, often creating multiple versions with subtle variations in length and thickness for different purposes. Scientists documented crows fashioning hooked implements from pandanus leaves, straightening them with careful movements, and then setting them aside in a kind of mental inventory for future use, suggesting a capacity for planning and abstract thinking that we typically associate only with primates and humans. The psychological mechanism underlying this behavior appears to involve what neuroscientists call executive function, the ability to envision a problem, imagine a solution that doesn't yet exist in physical form, and then manipulate the environment to bring that imagined solution into being. Crows possess large brains relative to their body size, with neural structures dedicated to problem-solving and innovation, and their frontal regions show activity patterns similar to those observed in human beings engaged in creative tasks. Beyond merely observing their environment and copying what they see, crows appear capable of what researchers term causal reasoning, understanding that certain materials have properties that make them suitable for certain tasks, and that modifications to these materials can enhance their functionality. What persists as genuinely fascinating is how these corvids continue to develop and transmit tool-making knowledge across generations, with young crows learning from their parents and then innovating upon these techniques, creating a genuine culture of tool use that evolves and adapts across decades and centuries, much like human technological advancement on an avian scale. Beneath the forest floor, in the dark and quiet soil where roots intertwine and decompose, there exists an elaborate network of fungal filaments that connects trees and plants across vast distances, a system so pervasive that scientists have begun calling it the Wood Wide Web. These fungal threads, called mycorrhizal networks, form symbiotic relationships with plant roots, extending the reach of a single plant's sensory and nutritional capabilities far beyond what its own biology could achieve alone. Through these underground pathways, trees appear to exchange resources and information, sharing nitrogen and phosphorus from one plant to another, transferring chemical signals that warn of insect attacks and disease, and in some cases, even appearing to nurture their own offspring by redirecting more nutrients toward younger or weaker members of their own species within the network. The fascinating aspect of this discovery is that it challenges our fundamental understanding of plants as simple, stationary organisms locked in competition with one another, suggesting instead that they engage in something resembling communication, cooperation, and even a form of collective awareness distributed across an entire forest ecosystem. The mechanism behind this network operates through basic biochemical principles and fungal biology that science has understood for decades, yet the implications of how extensively plants utilize these networks took researchers by surprise. The fungi receive carbohydrates from the plant's photosynthesis in exchange for improved nutrient uptake, a straightforward trade, but the network structure itself allows for far more complex interactions than simple one-to-one exchanges. When a plant senses herbivory or disease through chemical receptors in its leaves, it can transmit these distress signals through the fungal network to neighboring plants, which then upregulate their own defensive compounds before they are even attacked, essentially preparing themselves for threats they have not yet encountered. The persistence of these signals across the network, the specificity of resource allocation based on plant kinship, and the apparent intentionality in nutrient distribution all suggest layers of chemical communication, and perhaps even a form of plant-based cognition distributed across the network as a collective system. Beneath the forest floor, in the darkness where roots spread through soil and decay, exists one of nature's most intricate communication systems, a vast underground network that connects trees across seemingly impossible distances, allowing them to share resources, information, and even warnings about threats that exist far beyond what any individual organism could perceive on its own. When mycologists first began studying fungi in earnest during the 20th century, they discovered that the majority of trees and plants do not exist as solitary entities, but rather as participants in a symbiotic relationship with fungal networks, where thread-like structures called hyphae penetrate the soil and wrap around plant roots in arrangements so intimate that the boundary between fungus and plant becomes almost meaningless, creating a merged organism with capabilities neither could achieve alone. These fungal networks, which scientists call mycorrhizal associations, function as extensions of the plant's root system, dramatically increasing the surface area available for nutrient absorption, allowing trees to access phosphorus, nitrogen, and trace minerals that would otherwise remain locked in soil particles beyond the reach of their own root hairs. And in exchange, the trees provide the fungi with sugars produced through photosynthesis, fueling the fungal networks with energy they cannot generate themselves. What emerged from decades of research, particularly the groundbreaking work of forest scientist Suzanne Simard in the 1990s, was the revelation that these networks do far more than simply exchange nutrients on a one-to-one basis, instead forming vast interconnected webs that link hundreds or even thousands of individual trees together in what has been termed the Wood Wide Web, a name that captures both the structure and the function of these underground systems. Through these networks, trees appear to communicate in ways that defy our conventional understanding of plant behavior, sending chemical signals about insect infestations to neighboring trees, which then upregulate their own defense compounds in preparation for attack, and transferring excess nutrients from mature trees to struggling seedlings beneath their canopy, suggesting a form of parental care that persists even as competition for light and resources creates obvious evolutionary incentives for trees to hoard rather than share. In laboratories around the world, scientists have been observing a peculiar organism that challenges everything we thought we knew about intelligence and problem-solving. And this organism is not a brain at all, but rather a single-celled slime mold called Physarum polycephalum, which, despite having no neurons, no brain tissue, and no capacity for conscious thought, demonstrates an extraordinary ability to navigate mazes, optimize networks, and solve complex spatial problems with an efficiency that rivals or even surpasses computer algorithms designed by human engineers. When researchers place a slime mold in a maze with food sources at various points, the organism gradually explores the space, leaving behind a trail of protoplasm as it moves, and remarkably, over the course of hours or days, it finds the shortest route between food sources and consolidates its path into the most efficient network possible, essentially solving the maze in a way that minimizes energy expenditure and maximizes nutritional gain. The mechanism behind this seemingly intelligent behavior operates through a process of chemical communication and reinforcement rather than conscious deliberation, as the slime mold secretes biochemical signals that strengthen connections along successful pathways while allowing less productive routes to fade, creating a form of distributed problem-solving that emerges from the simple rules governing how the organism distributes and concentrates its cytoplasm. This behavior persists and continues to fascinate scientists because it reveals a fundamental truth about intelligence itself, suggesting that problem-solving capabilities need not require centralized processing or conscious awareness, but can instead emerge from decentralized systems where simple local rules give rise to globally optimized solutions. The slime mold's success has inspired computer scientists and network engineers to develop algorithms based on these principles, demonstrating that what appears to be unintelligent biological matter actually embodies a profound and elegant approach to optimization that has influenced human technology and our understanding of how complex adaptive systems can achieve remarkable feats without any cognitive machinery whatsoever. Perhaps most intriguingly, this discovery has fundamentally shifted how scientists conceptualize problem-solving itself, prompting researchers to reconsider whether intelligence might be distributed throughout nature in forms we have yet to recognize, and whether the humble slime mold might serve as a teacher for designing more resilient, adaptive systems in an increasingly complex world. Imagine yourself standing in a supermarket, facing a shelf of seemingly identical yogurt containers, each one promising different health benefits, and in that moment, you find yourself unable to decide which one to purchase despite having spent considerable time reading every label and comparing every nutritional fact. The uncertainty feels genuinely profound, as if you are caught between multiple possible states of mind simultaneously, and only when you finally reach out and touch one container, when you force yourself to make a decision, does the wave of indecision collapse into certainty. This everyday experience of human decision-making has inspired cognitive scientists and quantum physicists alike to propose an intriguing theoretical framework known as quantum cognition theory, which suggests that the human mind may operate according to principles that parallel the strange and counterintuitive laws governing the quantum realm. According to this theory, our thoughts do not exist in classical binary states of true or false, yes or no, but rather they exist in a kind of superposition, occupying multiple possible states simultaneously until the moment we consciously observe or decide upon them. When we contemplate a choice, our mind generates a probability field of all possible outcomes and considerations, much like a quantum particle exists in all places at once until measured, and this explains why decisions often feel ambiguous and why our preferences can shift dramatically depending on how a question is framed or what information we have just encountered. The mechanism behind this phenomenon appears to involve the fundamental structure of human consciousness itself, where attention and awareness function as the measuring device that collapses this mental superposition into concrete thoughts and decisions. Our brains do not process information through simple logical gates that produce deterministic outputs, but rather through patterns of neural activation that can maintain multiple contradictory representations until forced to commit. Furthermore, the theory suggests that human judgment violates classical probability theory in ways that are consistent with quantum probability, including violations of the law of total probability and the occurrence of interference effects, where the order in which we consider options actually changes our final preference in ways that classical logic cannot explain. Deep within the intricate architecture of the human brain, there exists a profound mystery that has captivated neuroscientists and philosophers alike, a mystery that challenges our fundamental understanding of how consciousness emerges from the physical matter of our neural tissue. The Penrose-Hameroff orchestrated objective reduction theory proposes something radical and deeply counterintuitive, suggesting that consciousness is not merely an emergent property of classical neural computation, but rather arises from quantum mechanical processes occurring within microscopic structures called microtubules that exist inside virtually every cell in our bodies. These microtubules are cylindrical protein polymers that form part of the cellular skeleton, and according to this theory, they serve as the actual substrates where quantum events generate the unified, integrated sense of awareness that we experience as consciousness itself. Roger Penrose, a renowned mathematical physicist and Nobel laureate, proposed that the human brain somehow harnesses quantum superposition and entanglement, allowing multiple possible states to exist simultaneously until a moment of collapse occurs, and this collapse represents the precise instant when we become consciously aware of something. Stuart Hameroff, an anesthesiologist and consciousness researcher, built upon these ideas by identifying microtubules as the likely location where such quantum effects could maintain coherence long enough to influence neural processing. The theory suggests that consciousness requires both the quantum effects within microtubules and the orchestration of these quantum states across vast networks of neurons, creating moments of sudden awareness rather than a continuous gradual process. This remains profoundly controversial because it contradicts the dominant view that consciousness arises simply from patterns of electrochemical signals firing across synaptic connections, and yet it persists in academic circles and continues to attract serious researchers who find in it explanations for phenomena that classical neuroscience cannot adequately address, such as the binding problem or the persistent mystery of subjective experience itself. While critics argue that the brain's warm, wet environment would cause quantum coherence to decohere too rapidly to be relevant, proponents counter that recent discoveries of quantum effects in biological systems, from photosynthesis to bird navigation, suggest that evolution may have found ways to harness quantum phenomena in ways we are only beginning to understand, making the theory less implausible than it initially appeared. Imagine you are sitting in a quiet room, and someone places a bright red apple on the table in front of you, and as light reflects off its waxy surface, your eyes capture that wavelength of approximately 620 nanometers, and this information travels through your optic nerve as electrical signals into your brain, where it activates specific neural pathways and neural networks. And through a cascade of biochemical processes, your brain constructs a representation of redness. A vivid subjective experience of what that color actually feels like from the inside of your consciousness. Now here is where philosophy enters the picture with perhaps its most stubborn and vexing question. Why does processing that light wavelength produce a subjective feeling at all? And why does your experience of redness feel like this particular quality rather than some other quality, or perhaps nothing whatsoever? This is the heart of what philosophers call the hard problem of consciousness, first formally articulated by philosopher David Chalmers in 1995, a problem that cuts to the very foundation of how we understand the mind and remains fundamentally unresolved despite centuries of scientific advancement and philosophical contemplation. The hard problem emerges because of a seemingly unbridgeable gap between objective physical facts and subjective conscious experience, or what philosophers call qualia. And while neuroscience can map which brain regions activate when you see red or taste chocolate or feel pain, it cannot adequately explain why these physical processes generate the felt quality of experience itself, the redness of red or the painfulness of pain. We can explain the function, we can measure the neural correlates, we can describe the information processing, yet the fundamental mystery remains. Consciousness persists as something that seems to require explanation beyond the boundaries of physics and neurobiology alone. What makes this problem particularly mind-bending is that most scientific endeavors proceed by breaking complex phenomena into simpler components. But consciousness appears to have an irreducible subjective dimension that resists this reductionist approach. And despite our astonishing technological capabilities and our deep understanding of brain chemistry, we remain fundamentally puzzled by the basic fact that we have subjective experiences at all. That there is something it is like to be you right now, experiencing these words and this narration, a quality of awareness that seems to demand explanation, yet continues to elude our most sophisticated scientific frameworks. Imagine sitting in a concert hall watching an orchestra perform, and as your eyes take in the scene before you, something remarkable is happening inside your brain that neuroscience still struggles to fully explain. The violin player on the left is wearing red, and you see the color, you hear the bright soprano notes, you feel the warmth of the stage lights, and you perceive the graceful movement of the bow across the strings. Yet each of these sensations is being processed in completely different regions of your brain simultaneously. The visual cortex handles the color and motion, the auditory cortex processes the sound waves, the motor cortex anticipates the movement, and multiple other specialized areas contribute their own processing, all happening in parallel, all distributed across different neural territories that have no direct connection to one another. This is the binding problem, one of the most profound mysteries in neuroscience and philosophy of mind. Your subjective experience is unified and seamless, that single coherent perception of the red violin and its sound, yet the neural mechanisms that create that experience are radically fragmented and dispersed. How does your brain take all these separate, distributed processing streams and combine them into the unified conscious experience you have of that moment? No one truly knows. When neuroscientists study brain activity, they find that different features are analyzed in isolation, processed by independent neural circuits, yet somehow you experience them as bound together into a single object or event. The color does not exist separately from the shape, the sound does not exist separately from the source, the movement does not exist separately from the performer, and yet neurologically speaking, they should, because the anatomical pathways that encode them do not naturally converge. Scientists have proposed various solutions to this mystery over decades, from the idea that synchronized neural oscillations might bind features together, to theories about attention mechanisms that select and integrate information, to notions of a global workspace where information becomes globally broadcast and thus experienced as unified. Yet none of these explanations are complete or fully satisfactory, and the mechanism remains one of neuroscience's enduring unsolved puzzles. What is perhaps most striking is how we live our entire lives without noticing this strangeness at all, without appreciating the profound logical impossibility embedded in every moment of perception, in every sight and sound and sensation that forms the basic texture of consciousness itself. Imagine for a moment that the color red, the way it appears in your conscious mind, has always been fundamentally different from the way it appears in everyone else's mind. Yet you would have no way of knowing this because you both learned to call that same wavelength of light by the same name. This is the essence of inverted qualia, a philosophical thought experiment that explores the mysterious gap between the objective physical properties of the world and the subjective, internal experience of consciousness that only you can ever truly access. Scenario typically begins with a simple premise. Suppose that one day, through some neurological accident or thought experiment, your color perception was inverted, so that where you once saw red, you now see cyan, where you once saw blue, you now see yellow, yet your brain's learned associations remain perfectly intact. So you still point to a stop sign and call it red because that's the word you learned to associate with that particular experience, even though the experience itself has completely changed. The deeper implication of this thought experiment is far more unsettling than the simple color inversion itself, because it suggests that two people could have entirely different subjective experiences of the same objective reality and never know it, never be able to communicate about it, and never find any external evidence that would reveal this fundamental difference in their internal worlds. The psychological mechanism that makes inverted qualia so philosophically troubling lies in what philosophers call the problem of other minds, which is the realization that you can never directly access the subjective experience of another consciousness. You can describe colors in terms of wavelengths and frequencies, you can map the neural correlates of color perception in the brain, you can even perfectly predict and explain all of another person's behavior regarding colors. Yet none of this necessarily tells you what the color experience actually feels like from the inside for that other person. This reveals a deep asymmetry in our knowledge of the world. We have direct, unmediated access to our own conscious experiences, which philosophers call qualia, but we have only indirect, behavioral and neurological access to the qualia of others. Imagine a person sitting alone in a closed room with only a piece of paper, a pencil, and a thick rule book written entirely in English. Outside the room, someone slides written Chinese characters under the door, and this person inside, who speaks no Chinese whatsoever, must look at the symbols, consult the rulebook which contains intricate instructions about which symbols to write in response to which incoming symbols, and then slide their answer back under the door. To the person outside receiving these responses, it appears as though someone inside understands Chinese perfectly well, because the answers are always contextually appropriate and grammatically correct. The rulebook is so comprehensive and detailed that every possible input has been accounted for with a corresponding output, creating an illusion of genuine comprehension and understanding of the Chinese language. This thought experiment was first proposed by philosopher John Searle in 1980, and it remains one of the most provocative challenges to our understanding of artificial intelligence, consciousness, and what it truly means to understand something at all. The mechanism underlying this argument cuts to the heart of a fundamental philosophical divide about the nature of mind and intelligence. Searle contends that following rules mechanically, no matter how perfectly and comprehensively, is fundamentally different from genuine understanding. The person in the room could execute the rulebook flawlessly without having any semantic comprehension of what the Chinese symbols actually mean, without grasping their significance or their relationship to real-world concepts. They are performing symbol manipulation, following syntactic rules, but they lack semantic content, the actual comprehension that would constitute real understanding. This challenges the assumption that artificial intelligence systems, which essentially operate by following computational rules and processing information according to programmed algorithms, could ever achieve genuine understanding or consciousness. The argument suggests that perfect behavioral replication of understanding is not the same as actual understanding, and that the subjective experience of consciousness involves something that mere information processing cannot capture. The Chinese room argument persists as profoundly relevant because it highlights an uncomfortable gap in how we define intelligence and consciousness that remains unresolved despite decades of technological advancement. Imagine sitting across from a computer terminal in a locked room, separated by a barrier from an unknown entity, and your only means of interaction is through a keyboard and screen where text appears before you. You begin a conversation with what you believe might be another human, or it could be an artificial intelligence designed to mimic human responses, and you have no way of knowing which one it truly is except through the quality and nature of the dialogue itself. This is the essence of the Turing Test, a thought experiment proposed by the British mathematician Alan Turing in 1950, which asks a deceptively simple question. If a machine can engage in conversation indistinguishable from a human being, should we consider it intelligent or even conscious? The test strips away all physical markers, all visual cues, all embodied characteristics, and reduces the entire question of artificial intelligence to a single metric: the ability to convince another thinking being that it too is thinking. The mechanism underlying this test operates on a profound philosophical principle: that consciousness and intelligence might not be tied to biological substrate at all, but rather to the functional capability of producing coherent, contextual, and convincing responses to questions and stimuli. When we interact purely through language without knowing the nature of what we face, our assessment must rely entirely on pattern recognition, on whether the responses follow logical threads, acknowledge context, demonstrate creativity, and exhibit what we might call understanding. The psychological dimension becomes equally important because humans are remarkably prone to anthropomorphization, to projecting consciousness and intent onto systems that merely simulate these qualities through sophisticated pattern matching. We find ourselves in a peculiar position where the Turing test simultaneously remains relevant and obsolete, where machines have become capable of passing many instantiations of such tests through large language models and neural networks. Yet we still argue endlessly about whether this demonstrates true intelligence or merely elaborate mimicry. The test persists in cultural consciousness not because it definitively answers the question of machine consciousness, but because it reveals something profound about human consciousness itself, that we cannot peer into another mind directly, human or otherwise, and that our certainty about others' inner lives rests always on inference and assumption. Consider the vastness of the universe for a moment, a cosmos containing hundreds of billions of galaxies, each holding hundreds of billions of stars, many of which we now know host their own planetary systems orbiting in the darkness of space. Given these almost incomprehensibly large numbers, the mathematical probability that Earth is the only planet to have spawned intelligent life seems vanishingly small, approaching zero when you account for the sheer abundance of potential habitats scattered across the observable universe. Yet when we look up at the night sky and listen carefully to the cosmic radio frequencies with our most sensitive instruments, we encounter nothing but silence, an absence of signals, no evidence of civilizations transmitting across the stellar distances, no megastructures, no waste heat signatures, no indication whatsoever that intelligent beings have ever looked back at us. This is the heart of the Fermi Paradox, named after physicist Enrico Fermi, who famously asked, "Where is everybody?" The paradox operates on a profound logical mechanism rooted in probability and expectation, creating a cognitive dissonance between what our mathematics suggests should exist and what our observations reveal actually does. We take the Drake equation, a mathematical framework attempting to estimate the number of communicative civilizations in our galaxy, and when we plug in even conservative numbers for the fraction of stars with planets, the fraction of those planets that develop life, and the fraction of life-bearing worlds that evolve intelligence, we arrive at figures suggesting millions or billions of civilizations should exist within our Milky Way alone. Yet our telescopes and radio arrays capture only an overwhelming silence, a void where contact should theoretically be screaming across the electromagnetic spectrum. The psychological weight of this paradox rests upon our deeply embedded assumption that abundance must produce visibility, that with such staggering numbers, surely some evidence should reach us, some accidental broadcast, some intentional message, some artifact of their presence. We have normalized this silence despite every logical expectation suggesting otherwise. We have constructed elaborate explanations and solutions to the paradox, rather than accepting the simpler truth that perhaps our intuitions about the universe are fundamentally incomplete. Imagine the universe stretching out in all directions, containing an estimated 2 trillion galaxies, each with billions of stars, and potentially trillions upon trillions of planets orbiting those distant suns. Yet when we look outward into the night sky and listen with our most sensitive radio telescopes, we hear only silence, profound and absolute silence. And this contradiction between the mathematical probability that intelligent life should exist elsewhere and the observable fact that we detect no signs of it whatsoever has come to be known as the Fermi Paradox. A puzzle so unsettling that it has spawned one of the most philosophically disturbing explanations in science, an explanation called the Great Filter. The Great Filter is a concept that suggests there must exist somewhere in the cosmic history, either behind us in our past or ahead of us in our future, some profoundly difficult evolutionary or technological barrier that life must overcome, a barrier so formidable that it either prevents life from arising at all, or prevents life from surviving once it has arisen, or prevents civilizations from spreading across the stars. And the very existence of this filter would explain why our radio telescopes have not yet picked up transmissions from alien civilizations broadcasting across the galaxy. Because if such civilizations existed in any significant numbers, their signals should already have reached us by now. And the mechanism underlying this reasoning is rooted in probability itself, in the understanding that if intelligent life were common, then statistically we should observe evidence of it, yet we observe nothing. Which means something is stopping life, something is filtering out the noise before it can reach us. In 2015, a star catalogued as KIC 8462852, located approximately 1,480 light-years from Earth in the constellation Cygnus, began exhibiting behavior that defied conventional astronomical explanation, and this phenomenon would become known colloquially as Tabby's star, named after Tabitha Boyajian. The Yale astronomer who led the research team that first documented these perplexing brightness fluctuations using data collected by the Kepler Space Telescope. What made this star so profoundly unusual was not a single dramatic dip in its light output, but rather an inexplicable and seemingly random pattern of dimming that could decrease its brightness by as much as 20% over periods spanning anywhere from mere hours to several weeks. Behavior that violated the fundamental principles astronomers had long used to classify and understand stellar objects. The traditional explanation for such dimming events in stars involves transiting exoplanets, massive celestial bodies that occasionally pass between their host stars and our telescopes, momentarily blocking small percentages of the star's emitted light in predictable recurring patterns. However, Tabby's star displayed dimming that appeared chaotic and without regularity, featuring dips of varying depths and durations that suggested no simple planetary explanation could account for the observations. This mystery sparked an extraordinary cascade of hypotheses and theories, with researchers proposing explanations ranging from swarms of comets with unusual orbital characteristics to fragments of shattered planetary systems still in the process of collapsing inward toward the star. Even more intriguingly, some scientists ventured into more speculative territory, suggesting that the dimming patterns might result from a massive artificial megastructure, such as a Dyson sphere or swarm of solar collectors constructed by an advanced civilization to harvest the star's tremendous energy output. The psychological mechanism underlying humanity's fascination with Tabby's star operates at multiple levels, beginning with our deep-rooted need to resolve anomalies and restore order to our understanding of the universe. When presented with data that contradicts established models, our minds naturally generate increasingly creative explanations to bridge the gap between observation and expectation. Imagine an astronomer sitting in a control room, watching data stream across monitors from a radio telescope pointed at the distant cosmos, when suddenly an alert appears indicating that a burst of radio waves has just arrived from billions of light-years away, lasting only a fraction of a second, releasing as much energy as our sun produces in entire days, and then vanishing into silence as mysteriously as it appeared. This is the phenomenon of fast radio bursts, or FRBs, one of the most perplexing discoveries in modern astronomy that fundamentally challenges our understanding of what exists in the universe and what forces could possibly generate such extraordinary power in such incomprehensibly brief moments. These bursts were first discovered in 2007 when astronomers analyzing archival data from radio telescopes realized they had captured something entirely unexpected, something that didn't fit into any existing category of cosmic phenomena that science had previously documented or explained. The signal itself arrives as an intense pulse of radio radiation that lasts only milliseconds, sometimes even just a few microseconds, making it extraordinarily difficult to detect and study since astronomers must be pointing their instruments in exactly the right direction at precisely the right moment to catch one. What makes these bursts especially mind-bending is that their sources remained completely unknown for years, leading scientists to propose increasingly exotic explanations ranging from neutron star collisions to civilizations transmitting signals across the galaxy. Yet the reality has proven to be something far more subtle and deeply strange. The mechanism that creates such enormous energy release in such tiny timeframes suggests the involvement of either extraordinarily dense matter, intense magnetic fields, or physical processes occurring near the event horizons of black holes. Yet no single theoretical framework perfectly explains all the observed characteristics of every burst that astronomers have managed to capture and analyze. Most intriguingly, astronomers have now detected bursts that repeat, coming from the same location in space multiple times over weeks or months, suggesting these events originate from persistent sources rather than one-time catastrophic events. Yet the variations in these repeating bursts indicate the underlying mechanism remains fundamentally different from anything we fully comprehend. Imagine the fabric of spacetime itself rippling outward like concentric circles spreading across the surface of a still pond, except these ripples move at the speed of light and carry information about the most violent events in the universe. And for nearly a century after Albert Einstein predicted their existence through his equations of general relativity, we had absolutely no way to detect them. No instruments sensitive enough to measure distortions in reality so infinitesimally small that they would change the distance between two objects separated by 4 kilometers by less than the width of a single proton. In 2015, scientists at the Laser Interferometer Gravitational Wave Observatory, or LIGO, finally achieved what had seemed impossible by creating the most sensitive measuring device ever built by human hands. And on September 14th of that year, they detected the unmistakable signature of 2 black holes colliding and merging over 1 billion light-years away. With such tremendous force that the gravitational waves they produced were so powerful that they could still be measured when they reached Earth despite traveling across the entire observable universe. What makes this discovery so conceptually troubling is that it required us to accept that gravity is not a force pulling objects toward each other, as Newton suggested, but rather a curvature of the very space and time that everything exists within, and that when massive objects accelerate, they don't just move through space, they actually deform the geometry of space itself, creating waves that propagate outward carrying information about the motion and energy of those objects. The psychological mechanism underlying our difficulty in comprehending gravitational waves stems from the fact that we evolved to navigate a world where gravity appears constant and unchanging, a background condition of existence rather than something that can ripple and wave like light or sound. Yet despite having no intuitive sense for how this could be real, despite the fact that our everyday experience provides no framework for understanding waves in the structure of reality itself, we have now built instruments that prove these waves exist and are being created constantly by colliding neutron stars and merging black holes throughout the cosmos. And we have normalized this impossibility by incorporating it into our understanding of the universe as simply another phenomenon waiting to be measured. Imagine standing at the edge of human understanding, where the invisible architecture of reality itself becomes tangible through mathematics and machines built to pierce the veil between the known and the unknowable. The story of the Higgs Boson represents one of science's most profound quests, a decades-long search for the answer to a deceptively simple question: why do particles have mass at all? For generations, physicists observed that some particles behaved as though they were heavy, while others seemed to drift through space almost weightlessly, yet no one could adequately explain the mechanism behind this fundamental property. In 1964, a Scottish physicist named Peter Higgs, along with several colleagues working independently, proposed a radical solution that would reshape our entire conception of reality. They suggested that the universe is permeated by an invisible field, what we now call the Higgs field, which exists everywhere simultaneously in every direction throughout all of space and time. This field is not something we can see or touch directly, but rather it functions like an omnipresent ocean through which all particles move, and when certain particles interact with this field, they acquire mass through this interaction, as though they were swimming through a dense medium that resists their motion. The more strongly a particle couples with the Higgs field, the more mass it possesses, making the field itself the source of inertia and heaviness in the universe. For nearly 50 years, this theoretical prediction remained purely mathematical speculation, an elegant idea without empirical proof, until scientists constructed the Large Hadron Collider near Geneva, Switzerland, a massive underground ring nearly 17 miles in circumference designed to smash subatomic particles together at nearly the speed of light. On July 4, 2012, after years of processing vast amounts of collision data, physicists announced they had detected the Higgs boson, the quantum particle associated with the Higgs field, confirming one of physics' most consequential predictions and earning Peter Higgs the Nobel Prize in Physics. This discovery validated an entire framework of understanding that had seemed almost miraculous in its precision, a concept so fundamental that it undergirds everything we perceive as solid matter in existence. Yet the discovery of the Higgs boson was not an ending, but rather an opening, raising new questions about why the Higgs field itself exists, what determines its strength, and whether deeper layers of reality await discovery beyond our current instrument's reach. Imagine a mystery so profound that physicists have spent decades searching for something that might not even exist, a particle so elusive that it could be passing through your body right now without leaving any trace of its presence, and yet its discovery would fundamentally reshape our understanding of the universe itself. This is the story of the Axion Particle, one of the most speculative yet theoretically compelling hypotheses in modern physics, a particle born not from direct observation, but from the elegant mathematics required to solve one of the deepest contradictions in our current understanding of nature. The axion emerged in the 1970s when physicists noticed a troubling asymmetry in the equations governing the strong nuclear force, the force that holds atomic nuclei together. These equations suggested that particles and their mirror images should behave differently in ways that should leave detectable traces in experiments, yet no such asymmetry had ever been observed, creating what became known as the strong CP problem, a riddle that refused to be solved by conventional means. In response to this theoretical crisis, physicist Roberto Pexi and Helen Quinn proposed a solution so economical and beautiful that it captivated the physics community, suggesting that nature must possess a new symmetry that automatically prevents this problematic asymmetry from manifesting. As a consequence of this symmetry breaking, a new fundamental particle would necessarily exist, and physicist Frank Wilczek named it the Axion after a laundry detergent brand, a choice reflecting the particle's proposed ability to clean up the theoretical mess in fundamental physics. The Axion would be extraordinarily light, perhaps billions of times lighter than an electron, and it would interact so weakly with ordinary matter that detecting it would require extraordinarily sensitive equipment capable of registering the faintest possible signals. Yet despite these staggering challenges, physicists have continued searching because axions might also solve another profound mystery: the nature of dark matter itself, that invisible substance comprising most of the matter in the universe whose gravitational effects we can measure but whose composition remains unknown. Imagine standing at the edge of human understanding, where physicists have proposed that our universe contains not 4 dimensions as we experience them, but rather 10, 11, or even 26 dimensions, depending on which version of string theory you examine. And most of these dimensions are theoretically rolled up so tightly at scales billions of times smaller than atoms that we cannot possibly perceive or measure them directly with any instrument we have ever created or could create. String theory emerged in the 1970s as physicists attempted to reconcile 2 of the most successful yet incompatible frameworks in all of science. Quantum mechanics, which governs the behavior of the smallest things in existence, and general relativity, which describes gravity and the structure of spacetime itself, and the theory proposes that what we call elementary particles, the fundamental building blocks of matter, are not actually point-like objects at all, but rather tiny vibrating strings of energy. And just as a guitar string can vibrate in different ways to produce different musical notes, these fundamental strings can vibrate in different patterns to create all the particles we know, including electrons, photons, and quarks. The reason string theory requires these extra dimensions becomes a matter of mathematics and consistency. For when physicists worked through the equations of string theory, they discovered that the mathematics only worked without producing infinities and contradictions if spacetime contained exactly 10 dimensions in the most common formulation. And these additional 6 dimensions, beyond our familiar 3 of space and 1 of time, must exist, but must be compactified or curled up at such incredibly small scales that they become inaccessible to our perception and measurement. What makes this conceptually challenging is that we have built our entire intuitive understanding of reality on the basis of the 4 dimensions we can interact with directly, and the human brain has no framework for genuinely comprehending what extra-spatial dimensions would feel like or how they would function. Yet physicists accept this framework not because it provides testable predictions we can currently verify, but because it represents the most elegant mathematical solution to one of the deepest problems in theoretical physics. And this acceptance reflects something profound about how science works at its frontiers, where empirical verification becomes impossible and mathematics becomes the primary arbiter of truth. Imagine standing at the edge of everything we know, looking out at a landscape so vast that our single universe becomes merely one grain of sand on an infinite beach. And this is the conceptual territory that physicists and cosmologists have begun to map with increasing seriousness over the past few decades. The multiverse hypothesis suggests that our universe, with all its galaxies and stars and the fundamental laws of physics that govern everything we observe, is not unique or alone, but rather one among countless other universes, each potentially operating under its own rules and containing its own versions of reality. The mathematics of quantum mechanics, when pushed to their logical conclusions, seems to demand this possibility, because when particles exist in superposition, in multiple states simultaneously, the most straightforward interpretation of the mathematics suggests that each possible outcome actually occurs in a branching universe of its own, meaning that every quantum event that could happen does happen somewhere in the vast expanse of reality. Similarly, the theory of cosmic inflation, which explains why our universe appears so uniform and flat despite its immense size, actually predicts that inflation did not stop after creating our Big Bang, but continues eternally in other regions of space, perpetually spawning new universes in an endless process of cosmic reproduction. What makes this hypothesis so peculiar is that it emerges not from wild speculation or philosophical musing, but from taking seriously the equations that have proven extraordinarily successful at describing reality, and yet the multiverse remains fundamentally beyond our observational reach, something we cannot see or touch or measure directly, existing instead as an abstract conclusion derived from the internal logic of our most successful scientific theories. The human mind grapples with this concept in an unusual way because, unlike other scientific discoveries that reveal hidden aspects of our universe, the multiverse hypothesis suggests that there may be aspects of existence that are permanently inaccessible to us, forever beyond the boundary where observation becomes impossible. And this creates a strange psychological territory where science approaches something that begins to feel almost like metaphysics or philosophy rather than empirical discovery. Imagine sitting in a darkened laboratory where a physicist prepares to conduct one of the most elegant thought experiments in human history, an experiment that seems to describe not just one reality, but an infinite branching tree of realities, each one equally real and equally valid, diverging at every quantum moment of choice or uncertainty. This is the essence of the many worlds interpretation, a framework proposed by physicist Hugh Everett in 1957, which suggests that every quantum event that could have multiple outcomes actually produces all of those outcomes simultaneously, each occurring in its own separate universe that branches away from our own. Traditional view of quantum mechanics, the Copenhagen interpretation, had long troubled physicists because it suggested that reality did not exist in a definite state until it was observed, that particles existed in a fuzzy cloud of probability, and that the act of measurement somehow forced nature to choose, to collapse from possibility into actuality. This seemed philosophically troubling, almost mystical, as though consciousness itself played a fundamental role in shaping the physical world. Everett proposed instead that the wave function, the mathematical description of all possible states of a quantum system, never actually collapses at all. Rather, whenever a quantum event could go multiple ways, the universe itself splits into separate branches, one for each possible outcome, and in each branch, observers experience a definite result that seems to them as though the wave function has collapsed, when in fact they are simply now living in the branch where that particular outcome occurred. Consider the famous thought experiment of Schrödinger's cat, where a sealed box contains a cat, a quantum particle in a superposition, and a mechanism that would kill the cat if the particle decays during a certain time interval. In the Copenhagen interpretation, the cat exists in a superposition of being both alive and dead until someone opens the box to observe it. In the many worlds interpretation, when the quantum system evolves, the universe splits into two branches. In one branch, the particle has decayed and the cat is dead, and in the other branch, the particle has not decayed and the cat remains alive, and both versions of the universe are equally real, containing versions of the observer and the cat experiencing the definite outcome in their respective branches. Imagine a laboratory where the present moment seems to reach backward through time to influence events that have already occurred, where a choice made today somehow affects measurements taken yesterday, where the arrow of causality appears to bend in ways that fundamentally challenge our understanding of how reality unfolds. This is the peculiar domain of retrocausality experiments, a frontier of quantum physics where researchers have conducted increasingly sophisticated tests, suggesting that future measurements can influence past outcomes, creating a tangled web of temporal causation that defies our intuitive grasp of cause and effect. One of the most famous examples is the delayed choice quantum eraser experiment, where physicists send individual photons through a double-slit apparatus, and then later, well after the photon has already passed through the slits and been detected on a screen, they make a choice about how to measure the photon in a way that seems to retroactively determine whether that photon behaved as a wave or as a particle back when it originally passed through the apparatus. The mechanism underlying these experiments rests on the peculiar properties of quantum entanglement and superposition, where particles exist in multiple states simultaneously until measured, and the measurement itself appears to collapse this superposition into a single definite state. But what makes retrocausality so conceptually unsettling is that quantum mechanics allows for these measurements to be performed in any order. And the mathematical framework suggests that the timing of when we choose to measure something does not fundamentally matter in terms of which version of reality becomes actualized. The equations work backward as well as forward through time, suggesting that information about future measurements can influence the probabilities of past events in a way that preserves the consistency of quantum mechanics, but seems to violate our deepest intuitions about temporal sequence. Yet despite decades of these experiments yielding results consistent with retrocausal interpretations, we have largely normalized this strangeness into the background of accepted physics, treating it as simply another unusual property of the quantum realm that does not require us to fundamentally reconsider how time itself operates, or whether the distinction between past and future is as absolute as we once believed. Imagine standing in a laboratory where reality itself seems to behave differently depending on when you observe it, and this observation can occur minutes or even hours after the original event has supposedly already happened. The delayed choice experiment represents one of the most philosophically unsettling demonstrations in quantum mechanics, one that fundamentally challenges our intuitive understanding of causality and the nature of physical reality. In this experiment, a photon or other quantum particle is sent through a setup with two possible paths, similar to the famous double-slit experiment, but with a crucial twist that makes it genuinely mind-bending. The scientist can choose whether to measure which path the particle took either immediately after it passes through the initial setup or delay that measurement until long after the particle has already traveled through the apparatus and created what appears to be a final result. What makes this experiment so deeply unsettling is that the particle seems to behave retroactively based on a choice made after it has already completed its journey. When the scientist chooses to measure which path the particle took, even if that choice comes after the particle has already interacted with a detection screen, the particle appears to have taken a definite path all along. Conversely, when the scientist chooses not to measure the path and instead measures something else, the particle seems to have traveled both paths simultaneously in a wave-like interference pattern. The mechanism underlying this phenomenon emerges from quantum mechanics' fundamental rules about observation and measurement, where the act of measuring a property fundamentally changes the state of what is being measured. The particle does not possess definite properties until measured, existing instead in a superposition of all possible states simultaneously. What bewilders us is how a measurement choice made after the particle has supposedly finished interacting with the apparatus can influence what appears to have already happened. Yet despite decades of experimental confirmation and theoretical refinement, we continue to grapple with the philosophical implications of this behavior. Some physicists propose that the universe might not have a definite past until observed, suggesting that reality only crystallizes into concrete facts at the moment of measurement, while others argue that quantum information travels backward in time in ways that preserve causality, though neither interpretation fully resolves the paradox that continues to captivate and perplex the scientific community. Imagine a laboratory experiment where light particles called photons are sent through two slits simultaneously, creating an interference pattern on a distant screen, the kind of wave-like behavior that suggests the photon traveled through both slits at once as a wave rather than as a discrete particle. And yet the moment scientists set up detectors to determine which slit each photon actually passes through, the interference pattern vanishes and is replaced by two distinct bands. As if the photon suddenly knew it was being watched and changed its behavior accordingly, a phenomenon known as wave-particle duality that has troubled physicists for nearly a century. The quantum eraser experiment takes this unsettling observation one step further by introducing a mechanism that allows scientists to erase the information about which path the photon took. And in a finding that defies conventional logic, when this erasure is performed, the interference pattern mysteriously reappears, as though the universe itself has forgotten that anyone was ever measuring which slit the photon passed through, suggesting that reality is not fixed until information about it is processed, that the past can be retroactively altered based on measurements made in the future, and that observation itself plays a fundamental role in determining what is physically real rather than merely revealing pre-existing facts about the world. The mechanism underlying this effect emerges from quantum mechanics' probabilistic nature and the concept of entanglement, where particles become correlated in ways that classical physics cannot explain, such that the act of erasing information about a particle's path causes its quantum state to revert to a superposition of all possible paths, allowing interference patterns to emerge from what should have been classical measurements. And yet this explanation, while mathematically rigorous and experimentally verified, still leaves us with the profound mystery that information itself appears to have a tangible effect on physical reality, that the universe seems to care about what we know and adjust its behavior accordingly, a principle so counterintuitive that it challenges our most basic assumptions about the nature of causality and the independence of reality from observation. Imagine two particles that have been created together, sharing a quantum entanglement that binds them across any distance, and now they are separated by miles or even light years. Yet when you measure a property of one particle, the other instantly responds in a perfectly correlated way, as if they are communicating faster than light itself, which should be impossible according to everything we understand about the nature of reality. In the 1960s, physicist John Bell posed a mathematical challenge to this phenomenon, creating what became known as Bell's theorem, which states that if quantum mechanics is correct and particles truly do influence each other instantaneously across vast distances, then certain mathematical inequalities must be violated in experimental results, meaning that the correlations between entangled particles must be stronger than any hidden variable theory could ever predict. For decades, physicists conducted increasingly sophisticated experiments to test Bell's inequalities, and in virtually every case, the results came back not in agreement with the classical view of reality, but instead violating Bell's inequalities, confirming that quantum entanglement does indeed produce correlations far too strong to be explained by any predetermined properties or hidden variables that the particles might have carried with them from the moment of their creation. What makes this violation so deeply unsettling is that it forces us to confront a universe that does not behave the way our intuition demands it should behave, a universe where distant particles can be correlated in ways that transcend our classical understanding of locality and causality, where the act of measurement itself plays a fundamental role in determining reality, and where Einstein's cherished principle that nothing can travel faster than light seems to apply to the transfer of information, while simultaneously allowing for connections between particles that operate outside the normal rules of space and time. The psychological mechanism at work here involves our deeply ingrained need to believe in a deterministic, locally real universe where objects have definite properties independent of observation, where causality flows smoothly from past to future, and where separate things remain truly separate until something physically connects them. Imagine two particles created together in a laboratory, then separated and sent in opposite directions across vast distances, perhaps one traveling to New York while the other travels to Tokyo, with no possible way for them to communicate with each other through any conventional means. When a scientist measures a property of the first particle, say its spin, the measurement somehow instantaneously influences the second particle thousands of miles away, causing it to take on a corresponding value in perfect correlation, a phenomenon that Albert Einstein himself found so deeply troubling that he called it spooky action at a distance. This is not merely a theoretical curiosity, but rather one of the most rigorously tested predictions in all of science, confirmed through countless experiments, including the landmark Bell test experiments that closed every conceivable loophole, allowing for hidden variables or conventional explanations. The mechanism underlying this phenomenon rests upon the principle of quantum entanglement, wherein particles become fundamentally connected in a way that transcends spatial separation, their properties existing in a superposition of all possible states, until measurement collapses this superposition for both particles simultaneously, regardless of the distance between them. This non-local connection does not violate Einstein's cosmic speed limit because no usable information can be transmitted this way. Yet the correlation itself appears to transcend locality in a manner that challenges our deepest intuitions about how reality must be structured. Despite decades of experimental validation and theoretical refinement, despite the fact that modern technology from quantum computers to quantum cryptography now relies upon this very principle, there persists among physicists and philosophers like a kind of unresolved cognitive dissonance about what non-locality truly means for the nature of reality itself. We have incorporated this seemingly impossible phenomenon into our mathematical frameworks and engineering specifications, treating it as a reliable feature of the quantum world rather than a paradox demanding resolution. Yet many still harbor the sense that something essential remains unexplained about how the universe permits such connections across the void of space. Perhaps the deepest insight is that non-locality forces us to abandon the notion of independently existing objects with definite properties prior to measurement, suggesting instead that reality at its foundation is fundamentally relational, with meaning and actuality emerging only through the act of observation itself. When the universe was born in the first fraction of a second after the Big Bang, something remarkable and deeply mysterious should have happened according to the laws of physics as we understand them. Matter and antimatter should have been created in perfectly equal quantities, emerging from the incredibly dense and energetic conditions of the early universe in a balanced dance of particles and their opposites. Antimatter is not merely theoretical or speculative. It is real, observable, and produced regularly in laboratories and naturally through certain radioactive decay processes. When a particle of matter meets its antimatter counterpart, they annihilate each other completely, converting their entire mass into pure energy in a violent and brilliant flash. If the universe had truly contained equal amounts of matter and antimatter in those first moments, they would have collided and obliterated each other almost instantaneously, leaving behind only energy, radiation, and empty void. There would be no stars, no planets, no galaxies, and certainly no observers to contemplate their own existence. Yet here we are, existing in a universe composed almost entirely of matter, with antimatter being extraordinarily rare and difficult to find. This asymmetry, this profound imbalance, represents one of the deepest questions in fundamental physics, a puzzle that physicists have wrestled with for decades without reaching a complete understanding. Various theoretical explanations have been proposed, including the possibility that antimatter and matter behave slightly differently under certain conditions, or that the early universe's violent processes created this imbalance through mechanisms we have yet to fully comprehend. Despite our scientific sophistication, our ability to probe the subatomic realm, and our mathematical frameworks that describe particle interactions with incredible precision, we still cannot fully explain why the universe contains anything at all rather than being perfectly balanced into nothingness. This asymmetry persists as a fundamental mystery precisely because it underlies the existence of everything we know, making it simultaneously the most obvious and most incomprehensible aspect of reality itself. The search for this asymmetry's origin has led physicists to propose exotic mechanisms like leptogenesis, where the decay of heavy particles in the early universe could have preferentially created more matter than antimatter, or to examine subtle violations of fundamental symmetries that might favor one over the other. In the beginning, according to our most refined understanding of physics, there was nothing. Yet somehow from that absolute nothingness, the universe emerged filled with matter, energy, and the fundamental particles that would eventually become stars, planets, and everything we observe today. This is the matter creation problem, one of the most profound paradoxes that sits at the intersection of physics, philosophy, and our deepest questions about existence itself. The problem emerges when we consider the laws of conservation that govern our universe, particularly the law of conservation of mass and energy, which states that matter and energy cannot be created or destroyed, only transformed from one form into another. This principle has been tested thousands of times in laboratories and has never been violated under normal circumstances. Yet it appears to have been violated at the moment of the Big Bang, when all the matter in the observable universe came into existence from what we believe was no prior matter at all. Our minds struggle to reconcile this contradiction because we have evolved in a universe where things always come from other things, where every effect has a cause, and where nothing appears without a source. The psychological mechanism behind this difficulty lies in our cognitive architecture, which is fundamentally designed to understand causality and continuity within the material world we inhabit. We cannot easily conceptualize true nothingness or absolute zero states because our entire framework for understanding reality is built upon observation and experience within a reality that already exists. Some physicists and cosmologists have proposed that perhaps the universe could emerge from quantum fluctuations in a pre-existing vacuum field, suggesting that true nothingness might never have existed at all, that there was always something even before the Big Bang. Others have theorized that the universe might be a closed system where the total energy is precisely zero, meaning that all positive matter and energy is balanced by negative gravitational potential energy, allowing the universe to emerge without violating conservation laws. These elegant solutions attempt to eliminate the paradox through mathematical and theoretical frameworks, yet they ultimately push the question back one step further, asking where the quantum fields or the mathematical laws themselves originated. What persists despite centuries of scientific advancement is our fundamental uncertainty about whether the question itself is answerable or whether it represents a boundary beyond which human understanding cannot venture. In the earliest fraction of a second after the Big Bang, something extraordinary is believed to have occurred in the fabric of spacetime itself, something so violent and expansive that it fundamentally shaped the universe we observe today, and the evidence for this cosmic inflation has emerged not from direct observation of that ancient moment, but from subtle patterns imprinted across the cosmos billions of years later. When astronomers examine the cosmic microwave background radiation, the ancient light that has been traveling toward us since the universe was merely 380,000 years old, they discover remarkable uniformity across every direction they observe, a consistency so precise that regions of space that could never have communicated with one another during the universe's infancy nonetheless possess virtually identical temperatures and properties. This uniformity presents a profound puzzle because, according to standard Big Bang theory alone without inflation, these distant regions should have developed completely independently, following their own physical trajectories without any mechanism to ensure they ended up so remarkably similar. The explanation that physicists have developed suggests that in the unimaginably brief period before the universe's first second elapsed, spacetime underwent exponential expansion, doubling in size countless times in succession, which would have stretched a tiny patch of the early universe outward so dramatically that the entire observable cosmos we see today represents merely one small portion of this inflated region. The evidence supporting this inflation model appears in the patterns of density fluctuations frozen into the cosmic microwave background radiation itself, which reveal precisely the kind of quantum fluctuations that would have been stretched to cosmic scales if inflation had indeed occurred, creating the seeds from which galaxies would eventually grow. Furthermore, the observations of the universe's geometry indicate that spacetime is remarkably flat, exactly what inflation theory predicts it should be, and the gravitational waves detected by advanced observatories show polarization patterns consistent with inflation's predictions, creating an increasingly robust body of indirect evidence that points toward this extraordinary event. Deep in the cosmic microwave background, that ancient light left over from the Big Bang itself, astronomers have discovered something that shouldn't exist according to our current understanding of the universe, a region of space remarkably colder than everything around it, a patch of sky that has come to be known as the cold spot, and this anomaly has puzzled physicists and cosmologists for nearly 2 decades now. The cosmic microwave background is the oldest light we can observe, radiation released when the universe was merely 380,000 years old, a time when hydrogen atoms first formed and light could finally travel freely through space instead of bouncing off charged particles in every direction. This ancient light arrives at Earth from all directions, and when we measure its temperature incredibly precisely using satellites like the Wilkinson Microwave Anisotropy Probe, we find that it averages to approximately 2.7 Kelvin, just barely above absolute zero, which is exactly what we would expect from a universe that has been expanding and cooling for nearly 14 billion years. However, when astronomers examined detailed maps of this radiation, they noticed that one particular region, a patch of sky about 10 degrees across in the direction of the constellation Eridanus, appeared distinctly colder than its surroundings, approximately 70 microkelvin cooler, which sounds infinitesimal but represents a significant deviation in the context of cosmic measurements and statistical analysis. This cold spot is genuinely puzzling because according to our models of cosmic inflation and the Big Bang, the early universe should have been almost perfectly uniform with only tiny random fluctuations scattered throughout. And while we certainly expect to find some regions hotter and some regions colder than average, the cold spot appears to be more extreme than probability alone would predict. Physicists and cosmologists have proposed various explanations, some suggesting that the cold spot might be the gravitational effect of an enormous void in space, a region with far fewer galaxies than average that would cause light passing through it to lose energy and appear cooler to us, a phenomenon called the integrated Sachs-Wolf effect. Others have speculated about more exotic possibilities, including the idea that the cold spot might be evidence of collisions with other universes at the edges of our own cosmos, a notion arising from some interpretations of multiverse theory, though this remains highly speculative and faces significant theoretical challenges. Imagine standing on the surface of Earth and looking out toward the horizon, where the sky meets the land in what appears to be a perfectly flat line stretching endlessly in every direction. And this simple observation has shaped human civilization for thousands of years despite being fundamentally incorrect. The flatness problem refers to our deep cognitive bias toward perceiving the world as fundamentally flat, a perceptual illusion so powerful that it shaped our understanding of geography, cosmology, and even our place in the universe for millennia. Our eyes, which evolved to navigate relatively small distances across terrestrial landscapes, are exquisitely designed to detect danger and opportunity within a few hundred meters, and within that limited scope, the curvature of a sphere with a radius of 6,000 kilometers becomes completely imperceptible to our direct sensory experience. When you look across a field or a valley or even an ocean, your brain receives visual information suggesting flatness because the curvature happens at scales far larger than your visual system can resolve, and your neural architecture, having evolved under conditions where this assumption worked perfectly well, simply accepts this conclusion without questioning it. The psychological mechanism underlying this bias involves what neuroscientists call frame of reference scaling, wherein our brains construct models of reality based on the spatial scales most relevant to survival and reproduction. And since humans spent hundreds of thousands of years moving across relatively small patches of landscape, our perceptual systems optimized for flatness at those scales rather than for the actual spherical geometry of the planet. What makes the flatness problem particularly fascinating is how it persisted even as human civilization developed the intellectual tools to discover and prove the spherical nature of Earth. For ancient philosophers and later medieval scholars had mathematical and observational evidence that the world was round, yet this knowledge struggled to penetrate public consciousness and cultural imagination. Despite having access to the same evidence, common people continued to imagine Earth as fundamentally flat because the perceptual evidence of their everyday experience contradicted the abstract mathematical conclusions, and human psychology has always given greater weight to direct sensory experience than to theoretical reasoning. Imagine standing on a beach on a perfectly clear day, looking out across the ocean toward the distant horizon where the sea meets the sky, and notice how that line appears to curve slightly downward away from you, as though the world drops off into an abyss just beyond your vision. This visual phenomenon, known as the horizon problem, has shaped human consciousness for millennia, creating a persistent illusion that contradicts what we now understand about the actual shape of our planet. The horizon presents itself to our eyes as a flat or slightly curved boundary, a demarcation line that creates an intuitive sense that we stand at the center of a flat or dome-like world, with everything else sloping gently away from our position. This perception feels so immediate and so real that it requires a conscious intellectual effort to override it with the knowledge that we actually inhabit a sphere, and that the curvature we perceive is merely a function of our limited vantage point relative to the vast scale of Earth's diameter. The mechanism behind this persistent illusion lies in the way our visual system processes distance and perspective. When we look toward the horizon, our eyes receive light that has traveled across the curvature of Earth, but because our eyes occupy such a tiny point on such an enormous sphere, the actual curvature is vanishingly small from our perspective. Our brain interprets distant objects as appearing smaller and hazier due to atmospheric perspective and the limitations of human vision, and this naturally creates the impression of a flat plane extending infinitely outward. Furthermore, our evolutionary history as terrestrial creatures adapted to perceive a human-scale environment means our visual intuitions are calibrated for distances measured in hundreds of meters, not thousands of kilometers. So at the scale of planetary curvature, our perceptual systems simply cannot directly detect what is actually there. What makes the horizon problem so philosophically interesting is that despite centuries of scientific evidence, despite photographs from space showing Earth's spherical form, despite the ability to circumnavigate the globe and return to where we started, many people still feel an intuitive doubt when confronted with the horizon. This suggests that direct visual experience and embodied perception exert a powerful hold on human belief that persists even when it contradicts abstract knowledge and empirical evidence, revealing a fundamental gap between what we know intellectually and what we can genuinely feel to be true based on sensory experience alone. Deep within the universe's most fundamental measurements lies a contradiction so persistent and troubling that it has become one of astronomy's greatest unsolved mysteries, a phenomenon scientists have named the Hubble Tension. The situation unfolds like this. Astronomers have developed two independent and seemingly reliable methods for measuring how fast the universe is expanding, a rate known as the Hubble constant, which fundamentally determines the age, size, and ultimate fate of everything we know. The first method involves examining the leftover radiation from the Big Bang itself, the cosmic microwave background, and using our understanding of physics to extrapolate backward and predict how quickly space should be stretching today. The second method relies on direct observation of nearby supernovae and galaxies, measuring their distances and velocities through the universe to calculate the expansion rate in real time. For decades, these two approaches stood in disagreement, but that disagreement has now become so statistically significant and so precisely measured that it cannot be dismissed as mere observational error or instrument miscalibration. One method suggests the universe is expanding at approximately 67 kilometers per second per megaparsec, while the other consistently yields roughly 73 kilometers per second per megaparsec, a discrepancy of about 9% that might sound small but carries enormous implications. The psychological mechanism underlying our relationship with this tension reveals something profound about how science operates in the modern age. We have become accustomed to believing that our measurements and our theories should harmonize, that reality has a consistency that our instruments can reliably capture, and that fundamental disagreements indicate either error or hidden knowledge waiting to be uncovered. Yet the Hubble tension persists despite billions of dollars in observation, despite teams of the world's most brilliant cosmologists working on the problem, and despite no obvious candidate for resolution emerging from theoretical physics. We have somehow normalized this profound confusion at the heart of our understanding, treating it as a puzzle to be solved rather than a fundamental crisis, perhaps because we have learned to live with mysteries in an increasingly complex universe. The world is facing a paradox of its own making, one that becomes more apparent each year as our dependence on portable technology and renewable energy systems accelerates beyond what many anticipated. Lithium, a soft alkali metal that sits near the top of the periodic table, has become absolutely essential to modern civilization, yet the extraction and processing of this element creates a cascade of environmental and social consequences that most consumers never fully consider. Lithium is the primary component in the rechargeable batteries that power everything from smartphones and laptops to electric vehicles and grid-scale energy storage systems, making it arguably the most important mineral of the 21st century. And yet the methods we use to obtain it involve either mining hard rock deposits in places like Australia and Canada, or more commonly, evaporating massive quantities of lithium-rich salt brine in the Atacama Desert of Chile, the Salar de Uyuni in Bolivia, and various salt flats across Argentina and Tibet. These evaporation processes require enormous volumes of water in regions that are already experiencing severe drought conditions, and the extraction of a single ton of lithium can require up to 500,000 gallons of water, effectively draining aquifers that indigenous communities have depended upon for centuries and transforming entire landscapes into industrial zones. The contradiction lies in what we are told this technology is meant to accomplish. We are transitioning away from fossil fuels to protect the environment and preserve freshwater resources for future generations. And yet the very batteries that enable this transition are consuming precious water at unprecedented scales while creating toxic brine lakes and contaminating the soil with magnesium, potassium, and boron. Moreover, the mining operations themselves often operate in regions with minimal environmental regulation, weak labor protections, and limited governmental oversight, meaning that the true cost of our digital and electric lifestyle is externalized onto some of the world's most vulnerable populations, who receive minimal compensation for the resources taken from their lands. What makes this problem psychologically interesting is how completely invisible it remains to the end user, sitting comfortably in a developed nation using a smartphone or driving an electric car, feeling virtuously aligned with environmental values, completely unaware that their choices are participating in a different form of resource extraction that simply displaces harm to distant communities rather than eliminating it. When astronomers first began measuring the rotational speeds of distant galaxies in the early 20th century, they made an observation that should have fundamentally challenged our understanding of gravity and the cosmos. Yet it took decades before the scientific community fully grasped its implications. As telescopes improved and measurements became more precise, researchers noticed something profoundly troubling. The outer regions of galaxies were rotating far too quickly relative to the visible matter we could observe. According to Newton's laws of gravitation and Einstein's relativistic framework, galaxies should rotate more slowly at their edges, similar to how planets orbit the Sun with decreasing speed as they move farther away. The gravitational pull from a galaxy's center should diminish with distance, and therefore the stars and gas clouds in the outer regions should move more slowly than those orbiting closer in. However, observations revealed something entirely different, something that should have stopped the entire field in its tracks. The rotation curves of galaxies remained remarkably flat, meaning stars at the periphery moved nearly as fast as stars much closer to the galactic center, defying every prediction mathematics and gravity theory could offer. This anomaly emerged not as a minor discrepancy or a measurement error that could be corrected with better instruments, but as a persistent, universal feature observed in galaxy after galaxy, regardless of type, size, or composition. The implications were staggering and deeply unsettling for physicists who had spent careers refining gravitational theory. If the visible matter and known forces were insufficient to explain galactic rotation, then either our understanding of gravity itself was fundamentally incomplete, or something invisible permeated the universe in proportions far exceeding all the stars and planets we could see combined. The mechanism driving this phenomenon points toward dark matter, an invisible substance that comprises roughly 85% of all matter in the universe, yet remains undetected by direct observation. Dark matter creates an invisible halo surrounding each galaxy, its gravitational influence providing the additional mass necessary to keep rapidly rotating outer regions gravitationally bound. Without this hidden material, galaxies should have torn themselves apart billions of years ago, with stars flung into the void by centrifugal forces that no visible matter could counteract. In the early 1970s, humanity launched two remarkable spacecraft into the vast darkness of space, the Pioneer 10 and Pioneer 11 missions, designed to explore the outer reaches of our solar system and venture beyond into the interstellar medium. These robotic explorers were equipped with sophisticated instruments and golden records containing sounds and images from Earth, meant as messages to any potential extraterrestrial intelligence that might one day encounter them. For decades, these spacecraft traveled faithfully away from our sun, their trajectories carefully calculated and monitored by NASA scientists who tracked their positions with extraordinary precision, using radio signals transmitted across the immense distances of space. However, beginning in the 1980s, astronomers and engineers noticed something profoundly peculiar and deeply troubling about these spacecraft that defied easy explanation. The Pioneer probes were slowing down in a way that could not be accounted for by any known gravitational forces or recognized celestial mechanics, experiencing a slight but consistent deceleration that seemed to pull them gently backward with an acceleration of approximately 190 nanometers per second squared. This phenomenon became known as the Pioneer Anomaly, and it represented one of the most perplexing mysteries in modern space exploration, a small but measurable discrepancy that suggested either unknown forces were at work in deep space or there existed a flaw in our fundamental understanding of physics itself. Scientists proposed countless explanations for this mysterious deceleration, ranging from unaccounted gravitational influences from unknown planets or massive bodies lurking in the outer solar system, to exotic new forces that might govern the behavior of objects at vast distances from stars, to the possibility that our equations describing gravity itself might require fundamental revision. The anomaly persisted as an unsolved puzzle for more than 2 decades, captivating the imagination of physicists and engineers worldwide, each contributing theories and hypotheses to explain why these human creations should behave in such unexpected and perplexing ways. Yet through the patient work of scientists examining spacecraft telemetry data with meticulous care and investigating thermal emissions from the radioisotope generators aboard the probes, a more mundane explanation gradually emerged, one that revealed how the spacecraft themselves were subtly influencing their own trajectories through the radiation of waste heat away from their instruments and equipment. When spacecraft journey through the gravitational fields of planets, physics tells us precisely how they should behave, their trajectories calculated with extraordinary precision by teams of engineers who have spent decades refining our understanding of celestial mechanics. Yet beginning in the 1990s, something peculiar started happening with certain spacecraft as they conducted gravitational assist maneuvers around Earth, those carefully orchestrated flybys where a planet's gravity gently accelerates or redirects a spacecraft without using fuel. NASA scientists noticed that some of these spacecraft, including NEAR Shoemaker heading toward the asteroid Eros and Galileo on its way to Jupiter, would emerge from their Earth flybys with slightly different velocities than Einstein's equations and Newton's laws predicted they should have, sometimes gaining unexpected speed or losing it in ways that seemed to violate everything we understood about energy conservation and gravitational interaction. The anomalies were small, typically only millimeters per second, but in the precision world of space exploration, where even tiny discrepancies can accumulate into significant navigational errors, these unexplained variations sparked intense scientific investigation and debate about whether something fundamental in our physics was incomplete, or whether measurement errors and unknown factors were simply creating illusions of anomaly where none truly existed. The psychological mechanism underlying why this anomaly has persisted so stubbornly within the scientific community involves our deep confidence in mathematical models that have proven spectacularly accurate for centuries, creating a kind of cognitive dissonance when observations dare to contradict those elegant equations, because scientists have become accustomed to assuming that sufficiently advanced measurements must be capturing reality as it truly is. Yet simultaneously, they must entertain the possibility that their instruments might be recording subtle environmental effects not yet accounted for in theoretical frameworks, or that relativistic corrections and solar-wind interactions might explain away the apparent discrepancies if only they could be quantified with sufficient precision. In 1960, a physicist named Eugene Wigner published an essay that would become one of the most contemplative questions in the history of science, asking why mathematics seemed to describe the physical universe with such devastating accuracy and precision despite being a purely abstract human invention that emerged from our minds rather than from nature itself. When engineers design bridges, they use equations derived from abstract mathematical principles that were developed centuries before anyone thought about structural integrity or load bearing. Yet those bridges stand perfectly, defying any logical reason why invented symbols and operations should dictate the behavior of physical matter. When physicists predicted the existence of the Higgs boson using only mathematical formulas and theoretical calculations, and then actually discovered it in the largest particle accelerator ever built. They were essentially validating that abstract human thought had penetrated deeper into reality than any direct observation could reach, suggesting that mathematics exists in some fundamental way prior to our discovery of it. The mechanism behind this unreasonable effectiveness rests on a peculiar fact about human consciousness and perception. We are pattern-recognizing creatures whose brains evolved to detect structures and regularities in the world around us, and mathematics appears to be the distilled essence of pattern itself, extracted and codified into a language of symbols and rules that can be manipulated and tested for internal consistency. When a mathematician proves a theorem about abstract geometric shapes or numerical sequences, they are not inventing something new in any meaningful sense, but rather discovering necessary truths that must be true given the definitions and axioms they started with. And this discovery process somehow aligns perfectly with how physical reality actually behaves at the deepest levels.